with nearly 200 publications highlighting the significant impact of his work. He has also delivered more than 125 invited talks at the prestigious national and international platforms across countries such as USA, Singapore, Italy, Spain, and many more. He has successfully completed over 25 research projects and has served as an expert for esteemed organizations including DRDO and DST. He is also a reviewer for leading international journals published by Nature, Elsevier, RSC, IOP, and many others. One of his most notable achievements is the establishment of pioneering crystal lab for growing single crystal of technologically important materials, importantly particularly piezoelectric materials which have significant applications in green energy harvesting, beautifully aligning with the theme of this conference. We are truly honored to have such an academician with us today. Today, he will be delivering his keynote talk on piezoelectric crystals and nanomaterials for green energy harvesting. Now I humbly invite you, sir, to kindly address the gathering and share your valuable insights. May I also request the audience to welcome him with a warm round of applause.
Thank you, Dr. Niti, and all the organizers for inviting me here. The first good thing which I will tell you that my lecture was for 40 minutes, but I will try to complete in 25, maybe 20 minutes time, because it is already 1.5 hours late, so we must complete the things. So let's see how I can proceed. I will skip so many things, and I feel that many of the audience are students of this college. Some are PhD students, and mostly, can anybody tell me how many of you are from BSc level in this audience? Is there some students of graduation also?
Yes, sir.
Mostly others. Okay then, so I start with this. My topic is the green piezoelectric crystals and nanomaterials for green energy harvesting. So, देखो उसे move करना होगा, ये काम नहीं कर रहा. Okay, so plan of work is just, I will tell you something about my crystal lab. Then the topic is basically green energy harvesting. So the question is, what is the requirement of renewable energy? Next is some functional material I will define, then come to ferroelectricity and piezoelectricity. And then we will come to some results in respect of growth of piezoelectric crystals and nanoparticles, and how we use these materials to grow, to develop nanogenerators and energy harvesting. Next one. So I'm just skipping this slide that we do work on so many different materials, particularly piezoelectric material. In our crystal lab, we have many facilities, growth techniques and characterization facilities. Next one. So one question that my lab name is Crystal Lab. So why the name Crystal Lab is there and why crystals are important? So I will just summarize this whole screen that the crystal always represent the brighter part of our life. It is transparent, it is colorful, it is defect free, it is high strength, it is colorful, and so many things. So all those properties of nature are of good quality. So it means the crystal always represents the brighter part of our life. Next one. Now come to the main part, that why we require energy harvesting. The importance is this, that the whole energy sources, the conventional energy sources are depleting, and we need alternative sources. And it is very important not for our country but for the whole world and humanity. This slide is only there just to show that our country have recently initiated, recognized the importance of crystals growth within our country. So one of them is India Semiconductor Mission. It's a very high ambitious. You must have seen our Prime Minister inaugurating big factories, not factories, factories for developing single crystals for semiconductor only. And this semiconductor wafers are used for all the electronic devices. Come to the next slide. For a crystal, I can say that the crystals are important in the society because it is for ornament, for spiritual values. Oh no. So I am coming here. So the crystals are used at many parts for ornament, for spiritual values, for money, because normally crystals are very costly if it is of good quality. Then for our research purposes, then come to this side. This is our screen. It is based on crystal. This is the IC chip, which is all the electronic chips are actually wafers of semiconductor, silicon or some other devices. And one application is laser rod, which is a single crystal. Go to the next one. I have just shown some of the naturally grown crystals. Looks very good. That's all. Next one. This is also the crystals which are available, which are extracted from the nature, either within the ocean or deep inside the crust. Next one. And of course, diamond is there. This one is the skeleton of diamond that when we crystallographer study is a crystal, we go for the atomic level like this. Next one. So one question that if the crystals are available in the nature, why we want to grow? I think you tap it. So why we need to grow the crystal in the laboratory? The answer is that naturally grown crystals are good, but we need so many new materials, we need better quality, and that can be done only in the experimental labs. So we need to grow the crystals, and this is very good quotation that our technological development of a country is actually judged by the quality of single crystals we produce. Unfortunately, in our country, still we depend on so many other countries for single crystals for direct application. Next one. Now, why we need renewable energy? The answer is simple. That the normal conventional source of energy are depleting. Fossil oil is going down. Our population and demand are increasing. So we have to go for new and better, efficient source of energy. So what are the possible? So the problem with the conventional source is something like I have just summarized it. That when there is a coal, particularly, so there is a climate change, air pollution, demand, depression. So in the lower line, I have just mentioned what are the problems related with the conventional sources, rise in temperature, so many pollution-related deaths, and requirement of very high value of energy in the future. So we have to find out new sources of energy. Next one. So what are the sources which we call renewable energy? One is, we all know, there is solar energy, hydro energy, biomass, wind energy, geothermal, mechanical energy. So 5-6 different type of energies are there. And what is the name of or meaning of energy harvesting? So it is the energy harvesting is a process in which we create energy out of the available natural sources. Natural sources which if we do not use them, they will just go waste. For example, sunlight is there. If we draw the energy, we get find out the energy, electrical energy out of it, it is fine. If we don't do it, light is always there, it is going waste, that's all. Wind energy is there, wind is always there. If we take out some power of wind power to electrical, we can use it. If we do not use it, wind is always there, it will go waste. So the input is a energy which is naturally available, and if I take out some energy, nothing is going to happen with the nature. That's all. Next one. Now I will just come down to my main topic, nature. I am just walking, I am putting some pressure on this foot. My car is moving, so it is putting pressure on this. By some wind is moving on, and some mechanical energy is there. So we will just find out that how this mechanical energy can be converted to the electrical energy. That is the main work which I am going to elaborate. So some benefit of this piezoelectric, I will come to the word piezoelectric later on, that this type of energy is most abundant, it is independent of weather, very high number of users, and so on. Next one. In few slides, next one, just I will define the piezoelectricity. That piezoelectric material can convert mechanical energy into electrical energy. What does it mean? If I have a piezoelectric material and I will put a pressure on it, electricity will be generated. That's all. Next one. Now there is a comparison with different type of natural energies, piezoelectric, solar, wind, hydrothermal, fossil, and you will find that in all these 4-5 type of different energy sources, the mechanical energy is one which does not depend upon the weather, which never goes less. It does not depend on day or night. It does not depend whether wind is flowing or not flowing. So this is the last word is piezoelectric energy harvesting is the winner of all these 4-5 of things. One more problem. For example, I am taking a solar energy. I am put silicon big. After some time it go waste. So where you will deposit it? It is a very big challenge that if I have used and completed the life of a solar cell, solar panel, so where it will be thrown, because this is again going to be created other problem. Next go. So I have just compared different type of natural sources. So always piezoelectric energy. I will come to this later on. So here coal energy is always generous. So many fumes are there, coal is depleting, and so on. Next one. Solar, there is some problem with solar, that in night it is problem, weather dependent, storage is another problem, and so on. Next one. The same problem, some problem is there with the wind also, that it requires lot of open areas. It has a problem of storing the energy. So on. Next one. So I'm just coming to skip this slide. Next one. So with piezoelectric material, when we develop some device, that device is normally, if I am using a nanoparticles, is called nanogenerators. My whole work in this talk will be on this piezoelectric nanogenerator. So I will go to the different parts later on. The first thing that we use some nanoparticles or single crystals of piezoelectric material and make some device, and that device is called nanogenerator. I will just show you how it works and show the actual demonstration of the nanogenerators in this class. Next one. Next, skip. These are the slides that normally various type of applications are there. I'm not wasting time. I'm just converting my 40-minute lecture to 25-minute lecture. Okay, please bear with me. Next one. If you have any question, you can ask right now. Till this. No question? अरे स्टूडेंट्स को पूछना चाहिए. No. Next. Normally in normal lectures I do not go to the next slide unless I take one or two questions. Okay. So now come to the functional material. What do you mean by functional material? There are many properties, particularly piezoelectricity, ferromagnetism, ferroelectricity, pyroelectricity. I suppose that this audience understands this one. Piezoelectricity is the one where we get electricity just by application of pressure. Ferromagnetism, I think you understand. P loop, BH loop, you understand. Pyroelectricity is one where the change in temperature will create some electricity. Now, what is the meaning of functional material? These properties depend on temperature, depend upon pressure, depend upon the outer atmosphere, and so many other factors. So, if we are able to change this property with the help of temperature or pressure or some other, then that change can be used to develop some device. And that's why this material are called functional material. Next one. इसको skip कर दो. Next. I'm just trying to explain little bit this one. This is very, I think, familiar one. This BH loop or PE loop. In the case of BH loop, the same hysteresis loop is coming. In the case of ferroelectricity, the only Y and these two parameters are changed. Instead of magnetism, I get the polarization, and instead of magnetic field, it is electric. But this loop is there. Now, I will just try to explain you that what is the meaning of this loop and why it is so important. Okay? You see that this is one material, perovskite material, in which some polarization is there here. So this polarization is up, and in this side this polarization is down. What does it mean? That this polarization can exist in two states. Two states. Whenever we come across this word two states, means it is 0 or 1, that is all digital. So all the digital application which utilizes two states, good, bad, up, down, left, right, high, low, anything, that can be utilized for a digital application. And this PE loop, because it has two different directions of polarization, can be utilized for digital application. One. Second thing is, this energy is stored here. Energy is stored here. It means a PE loop, with the help of PE loop, we can store electrical energy which can be used subsequently. Next slide. These words I am not explaining. Now I will just show you that different materials show ferroelectricity, a loop which looks like same, but they are entirely different in terms of the magnitude, in terms of the nature. I will just show you some values here. This is for Jagano, where this value, I am not giving the name and units, etc. It is 0.01, it is polarization, 0.01, 0.03. This is for TGS, which is, it is 0.5, 0.1, 0.2. This is another one TGS, but some higher value, 2 or 3. This is the PMN lead-free material, where this polarization is 10, 20, 30. And this is PMMPT or BLFPT, where this is 60 or 70. What does it mean? That even if the loop looks same, the polarization value are entirely different, which can be utilized for further application. Next one. This is important. I will just tell you what is this. When I take a PE loop means I am changing the polarization with the help of electric field. So 1 cycle, 2 cycle, I can use 1 cycle for any application. But if I use 100 times, 1000 times, 10,000 times, this all properties should not change. All property means the retentivity here or coefficient force here. So you see that in this 10 to the power 7 cycles are there. But all those loops are almost overlapping. It means your material is not deteriorating in the continuous use condition. And this last one is the same thing. If I have plotted the polarization, this is retentivity, coercivity, then it is almost the same with the help of very large number of uses. Next slide. Leave it. छोड़ दो, 2-3 स्लाइड छोड़ दो पूरा. Now come to this. Now I will define what is piezoelectricity. Correct? Piezoelectricity means that if I have a material like this, I strike it and I will get electricity. Conversely, if I give a AC source on this material, we will get vibration. There are many simple applications. One, I will give one example of this. We all have a gas lighter in our house. So when you press it, there is a spark. What actually happens? There is a small piezoelectric material at the other end. When you strike it, there is some charge developed and which is used to light your gas. Second converse example is a quartz watch. You know that in the quartz watch we have a small button type of battery. So with this battery we give energy to your material, which is a single crystal of piezoelectric material, and that starts vibrating with a particular frequency. That frequency depends upon the size of the length of the crystal, and that vibration can be converted into the time zone in terms of the frequency with which it is vibrating. Next one. So the similar thing, I have just tried to explain it, that in a material which is non-centrosymmetric, I will just explain what is the meaning of non-centrosymmetric. That if a material has either cubic or rectangular or something, so all the positive charge ions and negative charge ion, normally their centers coincide with each other. So if the center coincide with each other, it is called a centrosymmetric. But if the centers are not coinciding, then there is a dipole developed inside. And that dipole will change if I change the dimension of the whole material. And because of that change, the dipole changes and the extra energy which is developed at the end points can be utilized for further purpose. Next one. So when we go for a piezoelectric material, we need two different properties. One is called piezoelectric charge coefficient, that is normally called P33, that is picocoulomb per Newton. What does it mean? That if I strike a material with some force, how many charge is developed? So that is in picocoulomb. So with the application of 1 Newton, how many charges are developed is your piezoelectric charge coefficient. So higher the piezoelectric charge coefficient, better is your material. Next one. Go to the next one. So here I have just already I have talked about, this is a simple lighting, this is watch, and this is a high-tech something. If you want, I can explain you a little bit, that this is a tip of a AFM, a microscope. AFM, you understand? Many of you. So that cantilever utilizes the piezoelectric effect, and because of that electricity we get the image. Next one. So there are many materials which we grow in our lab: organic crystals, lead-based lead-free crystals, and so many others. I will just show you that many piezoelectric materials which we grow in our lab, one by one. Next one. This is a single crystal growth mechanism of solution growth method, in which we grow the crystal by solution method. I am not explaining it, how it is growing and why it is growing. Just go to next slide to see the results. These are different crystals, mostly they are piezoelectric crystals. I am not going to give the name of all the crystals, but these single crystals, mostly they are piezoelectric, which can be used for any piezoelectric application. Next one. This is a name of another method, crystal growth, that is flux growth method. Again, I am not going to explain that how it is using different techniques to grow the single crystals. But we get the single crystals, very small thing I can tell you. We take the material in a platinum crystal, put in the furnace. That furnace, if the temperature is almost 1000 to 1400 degrees Celsius, and after some time we get a crystal something like this. Just show me the next one. So these are the single crystals which are piezoelectric, and we will show that how we use these crystals for application of the energy harvesting. Next one. This is another type of crystals we grow. This is not really, this is high DC superconducting crystals. This is PMMPT, PZMPT. This is PMMPT. All these materials are the materials which are highest value of D33. Now go to the next one. This is the third method which we use in our lab, is Czochralski method. I can just tell you last line that this is the method with which 90% of all the crystals which are used in industry are grown. We use this thing to grow the crystals of larger size. Next slide. So these single crystals are oxide crystals. These crystals are grown by Czochralski method. Next slide. Some other crystals. Next one. Now come to nanoparticles. We grow the nanoparticles by two methods. Starting from a bulk material, then grinding it to make nanoparticles of 100, 200, 300 nanometer size. And this is the method which is called bottom-up approach, in which what we do, we make a chemical reaction, and during the chemical reaction, crystal materials, atoms synthesize in the form of nanoparticles, and we use this thing for further application. Go to the next slide. Skip it. This is a chemical reaction which is taking place for the nanoparticles. Next one. These are the photographs of nanoparticles. I will just say that these are the plates. This size is about 20 to 30 nanometers. In this case, these are the nano rods, where this rod width is about 30 to 50 nanometers. This is mostly Jadano and some other materials. Next one. This is again nanoparticles. These are called nano sheets, where this is for Jadanas. They are also piezoelectric. Next one. So skip kar do isko. Skip. I will just show you and not explain that when we synthesize a material, what we do, we take up many characterization. One characterization is called structural characterization, in which we get whether the material is of the same phase or not, what is the A, B, C value, what is the other things. So we use XRD. Come to the next slide. Next. Then we make one more characterization which is related to finding out the particle size of the nanoparticle and whether these nano rods are single crystalline or not. Perhaps you will not understand, but I will just tell you that this shows a characterization where we get the average size. Here it is 79 nanometer, this is 123 nanometer, and in this study, the appearance of these small dots confirm that your particles are single crystalline nature. Next one. Next, sir. Next. Now, from here I will just show you the results. This is the very old one, 15-year-old. Here is your single crystals inside. This is a normal tapping key, and if I tap it, we get a voltage of say 68 millivolt. So this energy can be utilized just by tapping. Go to the next one. Now I will just explain that how the nano generators are fabricated. Okay, this is the nanoparticles. We dissolve with some solvent, and then we use a spin coater which rotates and give you some film type of thing. Then we use some other conducting material, ITO, PTO, make some contacts, something, and after so many different stages, we get a film with something like this, which is we call a nano generator. And this nano generator can be used to develop energy. How? These are the three different pictures of different publications, but mostly they are similar in nature. Next one. Now we have a nano generator, that is a thick film of say 1 centimeter to 2 centimeter. So if I strike it something like this, we can do the two things. Either we can take a single crystal as a whole and we can make a nano generator, a nanoparticle or a pallet. So you see that if I am using a single crystal directly here and fitting, I am getting a voltage of almost 50 volts somewhere it is written. Yeah, crystal is 50 volts. And if I use the ceramic, this 50 is the spikes of electric. And if I am using a ceramic, I am getting relatively less of the same material, just to establish that the single crystals exhibit much better electrical output as compared to ceramic counterpart. Next one. This is the device to apply mechanical force of different value, different force and different frequency. We put the material at this point and this strikes and we get the output electrical energy which can be recorded at a CRO. Next one. Similar thing, that if I increase the increase the mechanical force 0.4 kg to 1.2 kg to 2 kg, my electric output is continuously increasing 3.6, 26 to 52. It is quite logical that if I apply a higher and higher force, we will get higher and higher electric output. Next one. This is same thing, slightly designed as a generator. This is the change in the composition between the material, nanoparticles and the solvent. So there is a change in output. This is to show that if I strike it 1000 times, whether the output will remain the same or it will vary. You can see that if I take a small portion here, this electrical output is almost same. What does it mean? That if I strike it 100 times, 200 times, 1000 times, even then my electrical output will remain the almost same. Next one. Now come to the more recent results. I will just show you what is happening in this thing. मेरे बैग में देखना तो एक छोटा सा बॉक्स होगा. I will just show you how the nano generator which I fabricate is actually visible. वो उसके अलावा एक छोटा सा बैग. हाँ ये दे दो. I will just show you one. This looks something like this. You see that it is flexible. I can put it on here. I can put somewhere below my shoes. I can put on my throat. So when I speak, there is a vibration here, and this electricity can be generated. I put below my shoes. I will just show you what is happening there. I put this palm and I rotating my hand. Electricity will be generated. So magical. Now here it is this type of thing is there within the shoes. This is just walking. It is called foot striking, and 14 volts is generated. In this case, it is you put on a finger like this, like this, tape it and rotate your finger. So what happens because of this rotation, the lower part and upper part of this device is lengthwise changing, and which creates a lot of internal force, and that is sufficient to produce some electricity. In this case, last one it is like this. I keep it like this, and even this can generate some electricity. You can see that here in this case, of course, there 2.2 volt is there. So with the help of this type of electrical devices, with this one is 1, 2, 3, 4, 5, 6, 10, 20 LED, which glows when I strike my device. Next one In this case also, I will just show you that with another material, similar type of thing, almost 50 number of leads are there in one row and they all can grow. In this, what the students have done, they have removed the battery of the normal watch and then connect this thing through this output, and this for a moment, of course not continuously, but this can start working. In this case, it is slightly different one, that only with the bending of your hand, put it on your so your electricities are coming out one by one. If I put on a medical application, we can get the electrical thing. Next one. This what has done here, that if I put this nano generator at different parts of our body, correspondingly we get different values of electrical energy output. Next one. In a similar way, this particular device not only can be used to generate electricity, but it can be applied for some real time of application. In one case it is some security system, in some case it is some other. Last one perhaps, next one. In this slide also, few things are the same. The nano generator type of thing is actually put on different parts of the body and we get the electricity generated. Next one. The last one. I have just first time I am showing my all family, whatever I am with because of my students. So in 4 or 5 slides, this is of 2005 or 6. Those time my students. This is the latest one, my current students. This is during one function. You can recognize 2 of your teachers of this college in these photographs. Niti is there and Niti is here. Okay. And in one function, many of my students come with their family. So I have one photograph for them also. I always invite your college teacher or your students. You can come to my lab, want to do some work, you can do. If you want to just see something happening, how the crystals are growing, you can. And one beautiful thing is Delhi University or some universities this, that you need not require any permission from anybody. You can just walk into my lab, you can do some work and just go out. Thank you very much. If you have some question. How much time I have taken? 40 minutes.
Thank you for wonderful presentation. And a few questions to ask.
Yeah.
So you showed these electric crystals.
Yeah.
I want to ask you, how big are they? So when you make them using different methods, especially the flux method, you don't get really big crystals. So does it even matter for your applications for these electric materials? Do you get really big or small?
Yeah, I can tell you. The size of the crystal in general depends on the method on which we are doing. A solution flow crystal mostly are of 1 centimeter, 2 centimeter, not bigger than that, mostly 5 to 6 millimeter. A flux flow crystal are typically 5 millimeter across to 2 centimeter across, not bigger than that. A Tchaikovsky flow crystal in our facilities, we can grow up to 7 to 8 centimeters, but Tchaikovsky can be used to grow up to meters also, only matters. So, and of course, the crystal size depends upon the material of which we are doing. In a solution flow crystal, some crystals cannot be grown beyond 3 to 4 millimeter, and in some cases it can grow up to 1 to 5 centimeter. In my case, most of the piezoelectric flux grown crystals are 7 millimeter to 1 centimeter. Mostly they are 5, 6, 7 millimeter across.
I see that. So do you, I mean, I see that, most of the equipment that you're trying to make with them, you need small crystals, or like smaller and smaller crystals. Do you, if, let's say, so like in my work, we use flux growth when we make crystals, and we use Alawi, and we would use the Alawi to align the crystals to get a bigger crystal out of the smaller ones we've made. Can you also use this Alawi to make piezoelectric crystals, or would that affect the voltage that you receive?
Yeah, very good one. Two things, that this is ideally and this is possible, but in our lab we are not able to do the stacking of the crystals. We have not done, but most of the things which I have presented here is not on a single crystal, but it is on a nanoparticles used to make a thick film. Thick film means the thickness is maybe 0.5 mm, correct? And 1 to 2 centimeter across. So that is the one which we have discussed here. Most of the cases. Of course, we have shown that in case of single crystals, the output is much more, but that is not very practical way of using in daily life.
Thank you.
Actually, I have seen some of the materials using organic compounds. We have created flexible organometallic films or crystals. Like they mimic some properties of crystals, but they are not totally crystals. So, in that way, will piezoelectricity be produced in those organometallic materials?
Yeah. Actually, the extent of output will be different. If your crystal is not so good, for example, not so good means structure-wise not good or property-wise not good. Sometimes structurally defects are there, but the piezoelectric output remains, DC3 value remains the same. But organic crystals normally have a very low piezoelectric constant. TGS is one of the best, in which it can go up to 5 to 10 picocoulomb per Newton, maybe more after doping. But in most of the cases, 1 to 5 picocoulomb per Newton is the normal. While the PZ and PT or other single crystals are having almost 1,000 times more. 2,000 picocoulomb per Newton is typically a normal value for PZ and PT. So even if that material is bad, not so good, even you will get 400, 500 values. And a organic crystal, even if it is very good, you will get, instead of 5, you will get 8 or 10. That's all. Yeah. But one thing, if the DC3 value is not high, it does not mean that it is worthless. Why? Because ZNO normally is very low value of DC3. Normal way mein it is to few 1 to 2 or 3 or 5 picocoulomb. But it is the most versatile material to be utilized as a piezoelectric generator. That's it.
Thank you, sir, for such an interesting talk. It was nice to hear you.
Thank you.
The lecture was very truly inspiring. You explained with great clarity how piezoelectric materials and nanotechnology can be effectively utilized to advance sustainable energy solutions. It was indeed a remarkable blend of scientific depth, innovation, and a strong sense of responsibility towards our planet. I am confident that the audience present here must have gained valuable insights from your talk, which will undoubtedly contribute to advancing their research in the field of piezoelectric crystals and nanomaterials. On the behalf of the organizing committee, now I would like to express my heartfelt gratitude to you, sir, for your insightful and inspiring address. Your valuable thoughts, depth of knowledge, and innovative perspective have truly enriched this session and provided all of us with meaningful insights. It was a privilege to listen to your experiences and understanding in this field. We sincerely appreciate the time and effort you have taken to be here and to share your expertise with us. Your presence has added great value to this conference. Thank you once again for your gracious presence and making this session so engaging and enlightening. Now moving ahead, we are truly honored to have our keynote speaker, Professor Vinay sir, as a chairperson also to chair this session in this conference. I am confident that his insights and will greatly enrich this session. Now I request sir to kindly chair this session and guide the proceedings with his valuable presence. Over to you, sir.
Thank you. In this session, there are two invited talks and perhaps two oral presentations. The normal timings are 30 minutes each, but I just request you, because it is already 1.5 hours late, 40 to 30 minutes time can be converted to 20 minutes, please. I have also done some reduction. Okay, so just welcome Professor Alok Shukla. Please come. He is a professor of physics in IC Medicine. He is over 15 years of experience of teaching and research. He is a specialist in multi-media He has published more than 70 research papers and mentored large number of PhD students. The title is Unique and Structure and Functional Properties of Visible Complex Assigned by Layer and Coding. Please welcome Professor Alok. Thank you. Clapping. So,
Okay, sir, I will finish within time, don't worry. So, thank you so much. I am thankful to the organizer for inviting me. So, just I want to share you that I am coming from one of the farthest place, that Mizoram. Some of you might never heard the name also, I surprised. One place surrounded by Burma and another side is Bangladesh. Natural beauty is there, hill mountain, 6-month rainy season. Summer usually we have maximum temperature of 30-31 degree. So usually summertime I don't want to visit my hometown also. So with this, so that NIT was started in 2011 at Mizoram. I was one of the founder member of the physics department. So since 2011 I was working there. And I am thankful to my mentors and guide who have supported me to start the research work at one of the northeastern place. I want to convey my gratitude to late Professor R.N.P. Chaudhary, who was behind the inspiration to do the research in material science at Mizoram. Although I did my PhD in NMR, which is different from the what work I have started. So just I will present the brief work what we are doing, and then later if you have any query, question, then you may ask. So the main motto behind this talk is we are working on the multiferroics. So we have chosen the bismuth ferrite material. Some of them, those who are working on, you know that, very popular material, very common material, lot of papers are published, and people are doing either A side doping or B side doping, and sometime co-doping will be there. So people want to do the doping at A, B side also and see the property. And why we are doing so? Because our motto was to develop a material, as sir was discussing the single crystal, but our work is polycrystalline. So I never did work on single crystal. And second thing, it is a part of a funded project, so we want to develop a material, not device, So in future, if any engineer may test the material for fabrication, then they can do it. So what we did in this work, although I have started work till now, most of the PhDs were awarded on those material. So what work I am presenting here, it is basically on co-doping, where at the B side we dope the Ti and A side we dope the different rare earth. And why we have done it? Because if you know that leakage current is the major issue with a material like bismuth ferrite. So by doping, we want to check it whether we can reduce those value, we can increase the dielectric constant, so can the capacitor utility may be there. So this is the basic foundation of the work. So that what doping we have chosen, GD, LA and ND. So I just show you the result what we got it, and on the basis of some presumption about the work what we have done. So in multiferroics, if you see that we have, if you see that diagram, although sir has explained lot of things about the piezoelectricity, so that background I have already given. Sir has given the P loop also. It's not changing point. We just change the slide. No, change it. That to dielectric also know that. Just change it. Sir, this explain. This is for magnetism, as sir has ferroelectric explained P loop. Just this talk. So what we want to do it, if you see the multiferrocity means, on the application of applied electric field, polarization is there. On the application of magnetic field, magnetization is there. And then stress-strain relation is there. So that is the ferroelastic. So in our work, we have done this ferroelectric and ferromagnetic study, because this will be done by mostly the mechanical engineering people, but later we'll try to do it. So these are some basic types of multiferroics, type 1, type 2, if you see that. So this bismuth ferrite is type 1 multiferroic. So in type 1 we have done the doping, co-doping of Ti and rare earth. Please change. Yes, this we have done. Yes. Yes, so what we have done in the study, as sir was showing, for more structural study, we have done the XRD, then IC-SFAM study for the surface morphology, then EDX for the elemental, and then electrical properties we have done through the PSM. In electrical, we have seen the dielectric constant loss, impedance, how they are changing, then Coulomb plot, then the Debye equation, what they are following. And then finally, what result we got it, we compiled it, so we can say that this may be useful for that one. So we use the method which is known as solid state reaction. Same material you can prepare with the different methods also, like sol gel and any other, so that the methodology is little bit different. Just next view. So here this is the schematic flow chart is there, ki how you will do the preparation. So first we'll take the raw material, their stoichiometric ratio, then start calcination, and then mixing, grinding with the mortar and pestle. If you have ball mill, then you use ball milling also. And after calcination, if you see the phase curve formation, then you go for sintering also. And before sintering, if pelletization is required for electrical measurement, you can do the pelletization by using the hydraulic press. And once sample is prepared, then only the final characterization will come. So this is the overview of the method of solid state reaction technique. Then this is the equation involved in the GD modification, lanthanum or neodymium. Similarly, you can try with the some other rare earth also. And why we dope rare earth? Because if you see that bismuth is volatile in nature, so during heating lot of evaporation of the bismuth is there. So that's why while preparation you have to add little bit more bismuth in the material. So generally in our case we'll take extra 2% to reduce the evaporation part of it. Then schematic balancing equation is required, then balancing, and sometime deliberately you have to disturb the tolerance factor also. Because if you see the structure of any material, if you consider the ABO3 type structure or relaxal ferroelectric, etc., so then individual atom has its very specific position. So if atomic radii, if you are putting the external doping material where atomic radii is different from the parent material, ultimately you are putting distortion in the structure. So that's why ideally the tolerance factor value should be 1, and that is the ratio of ionic radii Ra by Rb root of R, this one. So you can calculate it. So once you disturb the structure, then it should be different from the 1 or lower than 1 also. So then by calculating it, you can show that this is the tolerance factor of the as prepared one. Next. And these are the techniques, as I told you, XRD and TEM for surface morphology. XRD is just like our fingerprint. Individual we are doing the fingerprinting for our identity. Similarly, if you prepare any material or compound, it has its own identity. So initially we will compare with the JCPDF, then IPDF there. So more than 2 lakh samples will be available there, database is there. So you can compare with the standard database. If you prepare new material, then the structure will be different. So you can predict the new structure of the formulated material, etc. So these are the XRD and then TEM for the surface morphology to show the polycrystalline nature of the material. Next. Then electrical studies, as I told you, we check the impedance measurement, dielectric constant, dielectric loss, then whether they are obeying the Debye or non-Debye type of relaxation, etc. Next. This is the instrument by we use dielectric measurement, that is PSM 1735. So other equipments are available. Next. This is for ferroelectric measurement, so we are using P-loop tracer. And then for ferromagnetic, that is vibrating sample magnetometer. Next. So what we did initially when we put the Ti on iron side and the GD on the bismuth side, and we did the grinding for 5 hours with the calcination and the sintering temperature of this, then we'll get the next. These are the XRD patterns which shows the structural analysis. We got the biphase sample where the previous. Yes, where the orthorhombic and cubic face is there, we have calculated the lattice parameter, GOF value, constant. So if you see the analysis, so their parameter can be found with the different software now available. You can do it with match software, Jena is there, retrieval refinement with the foolproof, etc. to confirm the phase conformation of the prepared material. Then this is the microstructural analysis for the as prepared sample. We have taken the 3 different series of the gadolinium where 10, 15 and 20% of GD is there. So we have find the average gain size of this micrometer order, and then we say, from this different shape and size of the material, we can say that the polycrystalline nature of the sample with that same study. Now this is the EDX analysis to confirm the atomic weight percentage. It shows that whatever the integrated constituents are there, like bismuth, gadolinium, iron, oxygen, and there is it's confirmed that there is a no foreign element present in the material. So you can confirm that the formation with the pure material of the whatever constituent is there. Next. These are the dielectric analysis. We have seen the dielectric constant and tangent laws. So if you see that initially at the lower frequency, the value of the dielectric constant is high, but the later it becomes almost constant. So because at the lower frequency, different type of polarization available in the material, so we will get the higher order of the dielectric constant, but later we'll get the only electronic polarization, so the value becomes lesser and finally constant. So this is the dielectric constant and loss analysis. Next. This is the with the temperature. Initially it was because we have restriction of our small furnace, so we cannot go beyond 400 degree. So later at the higher temperature we will get the phase transition or the phase transition temperature of the prepared material, but here it is not performed. Next. This is the impedance analysis. We have done the real and impedance, imaginary part of the impedance to show the Coulomb plot or the semicircle nature behavior of the to get the either Debye or non-Debye type of relaxation in the material. Next. So here if you see that this is the plot which is known as Nyquist plot or the Coulomb plot. This is relation between the complex and the real value of the dielectric constant. So by using the Jim Smith software, we can get that this shows the non-Debye type of relaxation because semicircular is different. And with this you can get the equivalent circuit model also. So give the real picture in terms of electrical parameter like resistance, capacitance, etc. So that part is not here, but in other study you may find that there is a equivalent circuit model which is a series or parallel combination of resistance and capacitance to show the realistic electrical parameter behavior of the material which is due to grain and grain boundary behavior. Next. This is the modulus, so it shows the multiple relaxation time of the material. So because multiple peaks you are getting with the index curve. Next. This is the AC conductivity because here we want to calculate the to show the PTCR or NTCR behavior whether it is present in the material. So in next slide if you see that we have identified the area. Next. Yes, here if you see that the different region we have marked in the activation energy curve, where we have calculated the activation energy which shows the NTCR or the semiconducting behavior of the material. So that is also a part of the study of this material. Next. This is the magnetic study. So here we got the some value of remnant magnetization which is different from the parent material. So we can say that after co-doping magnetic properties also little bit change from the parent material. Next. Similarly, we have done for PE loop also, but this is leaky nature or it's not giving the actual loop. Here our constraint is we cannot go beyond this 20 kilovolt per centimeter the applied electric field. So that is the maximum value. And another thing maybe the vacancies or the available in the prepared sample, so it will give the loosey behavior. But although we'll get the little bit value of the this one electric field in terms of the EC and P, that is different from the parent material. Next. So similarly we have done with the another doping of LA and the third one. So in all studies we have done the structural morphology, then electrical, then ferroelectric and ferromagnetic study to see the overall behavior of the material. So I am skipping because similar method is there, but only result is different from the previous substitution. Okay, please go ahead, change it. So this is XRD for it. Next. Next. Yes, similarly here SEM and EDX studies there. Okay, so I just directly come to the conclusion part. So all studies for the different series which we have done. So we have make it for the different sample and composition, and we have done the Ritchfield refinement with full proof, then dielectric with PSM, P-loop tracer study, then VSM used for magnetic or ferromagnetic study. So these results for the different series we presented. So why we have doing so? Because initially we started work with the A side doping of the bismuth ferrite, then later we'll do it with the B side doping also. Then we started co-doping. So we are using the plenty of data with the doping of the different composition. So later we are planning to do it with simulation or modeling for the device fabrication with the larger data, because now to everybody is using AI/ML technique to develop the devices. So I assigned some of the scholars, they started some work with AI/ML. So we compile all the data, so we'll come up with the modeling and simulation also. Here we have not done any optoelectrical property measurement, but if you are doping with the optical thing, so you can do the optical study like photoluminescence and others. So it depends upon the doping material and the available facility in the lab. So with that, I think I have, thank you, within time I have finished the presentation. So sorry because I have to go fast with the time constraint. So thank you for your attention, and if you have any query and question.
Thank you, Professor Alok, for completing the things in time. Thank you very much. I can take one question. If there is one. Yeah.
I'm very interested. I also work with bismuth and rare fuels. I want to ask a question. You mentioned how bismuth oxide is volatile. We face the same problem in our lab. I want to ask, how do you decide how much extra bismuth oxide you want to add? Do you see your impurity peaks? So for example, because we're working with polycrystalline materials, your impurity, whichever impurity bismuth creates, is inside your material. There's no way to separate that. So do you see it in your X-ray patterns? Do you see any impurity peaks in your X-ray patterns?
That's why I show in some of our work we have claimed that it is five-phase material, and commonly like selenite is also present in the specimen. We put star mark in the XRD, and it will be accepted because everybody knows.
Yeah, of course, yeah. But are you able to identify the impurity phases?
If you see that nowadays lot of reflection is there, because people have done lot of manipulation in XRD data.
Yeah.
If you see, I found two groups, one in Poland, one in Japan. They are identifying Indian researcher, and they give comment on the paper, so lot of reflection is going on. So that's why we are not hiding anything, whatever we are getting.
Thank you very much.
Thank you, sir.
So,
Nice to meet you, first time I meet you.
okay, thank you.
I will invite you to go.
So on behalf of this organizing committee, I am just presenting. How you will take it to middle.
It's heavy on whether it's line they will allow or not. I will give it to my student. He's also faculty here. He's
Yeah.
my student. Yes. He invited me for this talk. In 23 he joined.
So, there is a small change because of some urgency. Next talk is slightly shifted, and Ms. Simran Bhardwaj will present her work. The title of the talk is Synthesis and Characterization of Pure and CGS Signal.
Thank you, sir. Thank you for allowing me an very thankful to all the faculties of Shivaji College for inviting us here and organizing this such an insightful event, and this is going really well. And without taking much time, I will further proceed with my presentation. Already we are going quite short of time, so without wasting any time, let's come to it. I am Simran. I am pursuing my research in Interdisciplinary University of Technology, New Delhi, under the supervision of Dr. Harsh Yadav. And this is the outline of my work. And basically, we work on single crystals. And in this, for this presentation, what we have done, we have synthesized single crystals, and we have tried to dope the already very well-known crystal, TGS crystal. We have doped it with melchite grease dye to see the effect of that doping on the structural, optical, and the piezoelectric properties of the single crystal. Next. So what we do is we basically use slow evaporation solution method to synthesize it. Go to the next synthesis part. Yeah. Previous page. Yeah. So what we do is we have a single crystal, and we will see the effect of doping on the piezoelectric, optical, and the mechanical properties. And we can see that crystals, they are free of defects, and they are very good for the, they are free of grain boundaries, and so they are superior for their piezoelectric and optical properties, physical and chemical properties. That's why we, as sir said in his talk, so we need industries and we need work in the field of crystals in the laboratories to grow efficient crystals. So basically, here in my work, we are doing doping in the already made crystal, established ferroelectric TGS crystal, and we are doing next. Yeah, we are doing a doping of, you can see the right side, 0.02 mole % of melchite green dye was doped in already established. This is a very well-known TGS crystal, and we have tried to dope this with the Mg dye, and in the image we can see the successful incorporation of the melchite dye in the single crystal, TGS single crystal, because here there is no color, and in that image we can see color clearly. So, and in the XRD analysis, we see that there is not any change in the structural crystal system of the structure. It is monoclinic and belongs to the phase group 321, and we don't see any secondary phase here. No impurities, nothing is incorporated, so the structure is maintained. We are doing doping, but the structure is still maintained. There is no alteration in the structure. Next. And now what we did the piezoelectric charge coefficient, and we did it in Vinay sir's lab only. We are thankful to him for providing us this opportunity. And we got the D33 values, plus 8 for the normal, and plus 5.78 for the TGS MG dose. And here also we can see that there is a little bit change in the values, and this is because of the incorporation of the dye, because it changes word, and this is novel, and we have tried to do it. Thank you.
Thank you, Sonali. It was the first presentation. Even earlier also. Okay, so just you want to take one question? So one question other than yours. Anyone who want to ask any question? Please do.
This is not a significant difference, and there should not be any difference in the materials we are trying to go, because the molarity percentage is 0.02%. This is something very non-significant, but the results we are observing in FTIR, they are quite significant. But in optical properties, as you can see, the band gap also are getting same values. It is not. Yeah, and
Okay, thank you very much. Our next speaker is Professor Sonalika. She is an assistant professor in Hiroshima University, Japan, with over 13 years of international research experience. She specializes in designing functional nanomaterials, and she is a recipient of PhD Women Scientist Award and BRICS Young Scientist Award. So please welcome Professor Sonalika.
Hello everyone. I'm Dr. Sonalika from Hiroshima University. Okay, so due to the time constraint, as I mentioned that we have to be hurry. So firstly, I would like to thank the organizer for giving me the opportunity to come to my home country and present my work here. So today I'm going to show my work which I performed in IIT Jaipur, in South Korea, Spain and Hiroshima University. So today's topic is the advanced nanostructures metal oxide gas sensors for healthcare safety and environmental monitoring. So, as I am currently working in Hiroshima University, I think everyone heard Hiroshima and know the history of Hiroshima, right? So, anyone knows where this atomic bomb happened in Hiroshima? I think every student read in the history, right? Hiroshima, first city, atomic bomb. No one knows. At this year, okay. So in the 1945, the first atomic bomb on the Hiroshima, and this is the atomic bomb. Only the one building left after the atomic bomb. Okay. So this is a symbol of peace. So the Hiroshima University is a national research university which is established in the 1949. And this is the first atomic bomb striker city in the history of humankind. Right? So our Hiroshima University have a mission to contribute to the well-being of humankind
पीछे की वॉइस ज़्यादा आ रही है, पीछे की वॉइस ज़्यादा आ रही थी। अभी थोड़ा सा आवाज़ ठीक हुआ है, पीछे की जो बातें कर रहे हैं ना वो वॉइस ज़्यादा आ रही है।
Therefore, the gas sensing is very essential to ensure our safety, protect the environment, and support the clean energy, which improves our quality of life. So, I think for us, our life is most important than everything, right? So, we should focus on our safety and health. So, we need this gas sensor in our daily life. So, what is a sensor? Sensor is a very simple device. It can detect and respond to any type of input from the physical environment. Our body is a very good sensor, and our body has so many sensors. Right? We should thankful to God providing a very beautiful body which has so many sensors. But our nose, it fails. When it fails, when we are talking about the low concentration and when we are talking about the colorless, tasteless, odorless gases, that time our nose is failed. So we need an electronic nose or advanced gas sensors to detect this low concentration of the gases. I am working in the field of metal oxide gas sensors. Metal oxide gas sensors are known as Cami registers. Cami registers means the change in the resistance. What are the advantages? It includes the wide range of gas sensors, showing the high sensitivity, good selectivity, easy fabrication, less expensive, and very good operating life. Despite of the advantages, there are few major challenges with these MOS sensors. These MOS sensors are working at high operating temperature, which requires high power consumption, and it increases the cost of the device, and also it reduces the stability and life of the device. How we can improve it? There are so many ways to improve or to work on these challenges and can increase the sensitivity and selectivity of these sensors. Here is the basic gas sensing mechanism. It's a very basic mechanism. I think every student is a physics student and knows the semiconductor principle, right? Okay, so I will explain. It's very simple. What's happening here? When the gas sensing material comes into the contact with the air, then the material absorbs the oxygen, and this absorbed oxygen absorbs on the surface of the material by capturing the electron from the conduction band of the material. So now what happens? When electron comes from the conduction band, then what will happen? The resistance will decrease or increase? Yes, students. When the electrons comes from the conduction band of a material, then the resistance will increase or decrease? Simple. It's increase, right? So here, it depends. This mechanism, it depends. The material is N-type material or P-type material, or the gas is reducing gas or oxidizing gas. Here the mechanism is showing for the N-type material and for the reducing gas. So here in the picture you can see that in the presence of the air, the resistance is high. Now what will happen when this material comes into the contact with the target gas? Now these electrons react with that gas and release electrons. Now electrons goes back to the conduction band. It means the resistance decreases. This change in resistance is known as the response of a sensor. Simple. Right? The ratio of the change in the resistance is just known as the response of a sensor, or it is called as the sensitivity of a sensor. So here, this is the response. It depends, this is the ratio of RA or RT or over RT over RA. Depends on the type of the gas. There are so many parameters for the sensor. Not only sensitivity. faster response and recovery time, improve the sensitivity and selectivity, and also providing the long-term stability, which are the main parameters for a good sensor. So here is the first sensor. This sensor we developed in MNIT Jaipur. This is my first work in the sensing field. So here you can see the beautiful nano flowers. There are two types of flowers. One is the particle shape and second is the raw shape. So both flowers morphology confirmed by the SAM characterization. I will not go into the detail due to the time constraint. Again the morphology confirmed from the TAM. Here is the sensing device. This is the back side. It increases at a meter, platinum meter, and this is the ID, interdisciplinary network, where we are mounting our sample. How we are mounting the sample and preparing the sensing device. This is the before mounting the sample, and this is the after. So how the sensing device looks like this. This is the academic research. When we go for the commercial way, the size of the device definitely it should be compact. Okay, but this is the basic way, how we are preparing the device. So this is simply how much we are taking, just 10 to 20 mg materials, nanomaterials we are taking for the one device. These are the gas sensing results. So here, this is for the ethanol gas and this is for the anode. This is the reducing gas, as I mentioned earlier. Then for the reducing gas, when in the starting the resistance will be high, and in the presence of the gas, the resistance should be decreased. So it confirms the nature of the anti material. Here, if you should see the results, then both morphology showing the very good sensitivity up to the ppb level for the anode gas. But which one is better? The flower sensor is showing the high sensitivity in comparison to the nanorods because it's providing the high surface area, which is very important and providing the more active sites for the absorption and disruption process of the sensing. The next is the selectivity. Yes, this sensor is showing the good selectivity for the anode to gas, but as well as the rod are showing for the selectivity towards the ethanol gas. It's not good. Okay. Okay, sir, I will try to compare. Okay. So the conclusion is the morphology is also very important parameter, and based on that we can tune our sensing properties. Next sensor I will show mainly around the hydrogen. Everywhere the clean hydrogen, clean energy. So by increasing the demand of this hydrogen, there is an increase in water. There is an what is the problem with the hydrogen? The hydrogen is a very explosive, right? It's orderless, colorless. You feel like if there is a small leakage of detection, okay, there is a big explosion, big accident. So we need highly sensitive hydrogen sensor because this is the future, the hydrogen society, okay? These are another sensors based on the silver nanoparticles which improve the sensitivity and selectivity. I will skip. So basically for the hydrogen, the palladium is the very good catalyst. But with the palladium, the problem is the oxidation. So in this sensor, when we synthesize this sensor, the palladium is oxidized and it converts into the making the one junction, PN junction between PBU and zinc oxide. PBU is behaving as a P type, zinc oxide is behaving as an N type. Definitely, the sensitivity increases in comparison to the pure zinc oxide, but it also faces some issue because of this oxidation. So what we did, we applied the new strategy, which is the core-shell nanoparticle. In the core-shell nanoparticle, the core is fully protected by the shell and it prevents the agglomeration and detachment. So this core is fully protected and we can prevent the agglomeration and also we can prevent the oxidation of the palladium, right? Okay. So here you can see we have bimetallic and trimetallic some nanoparticles and yes, this is the core-shell nanoparticle. In this core, there are three elements, not single. There are three elements: silver, gold, and palladium. This is called the alloy. And this palladium, silver, and gold is a trimethyl nanoparticle. Is covered by the zinc oxide shell. Okay. So it's not agglomerated. It's not oxidized, which is confirmed by the XRD, XPS, correct additions. This is the gas sensing measurement. So here you can see, in comparison to the pure zinc oxide, the sensor response is only 4.9, and in the case of core shell, it increases to 4.8. So it approximately 85 times higher sensing response we observe. So by approaching this metal oxide nanostructures, we can achieve the ultra high response, excellent selectivity, low detection limit, good repeatability, and long-term stability. Here you can see there are so many cycles we tested for the sensor and showing the stable response. And the sensor also tested for up to 90 days. So there is very minimum change in the resistance and very minimum change in the response. And as well as clear selectivity towards the hydrogen we observe. This is the gas sensing mechanism. I will not explain. This is another one more application of this multifunction nanoparticle. Is not only limited to the sensing application. As the Professor Binet also explained, and they use zinc oxide nanoparticles for the other application. As well as I use this nanoparticles for the degradation of the methylene group. So, what is the conclusion? We need the next generation sensors. So, these nanostructures can offer the advanced capabilities for detecting the hazardous gases with the high sensitivity and the accuracy. These sensors also provide the superior performance and versatility to compare traditional gas sensing technologies. And also, these technology enable safer environment and support to the sustainability. What are the future direction in this area? Then still we are facing the problem with this MOS sensor is the high working temperature. These all sensors are working around 300 to 350 degrees Celsius, which is quite higher, and this temperature requires the more power consumption. So we need to reduce this temperature. So we are working in this direction. So low temperature operation. Now the world is towards the AI. So definitely we also need to improve our technology and connect with these sensors with the AI. We need multifunction platforms and the emerging materials with the new materials and innovation in this direction. So I hope very soon we also have this type of devices in our hand, in our bag, in this classroom, in our homes to prevent the what? Prevent the, yes audience, why we need gas sensors? Please students, yes. For the better health, for the good quality of their life, right? So definitely. I would like to acknowledge and be grateful to my professors, Professor Ichikawa, Professor Yonteyu, Professor Edward Robert, and Dr. Kamel Awasthi for the continuous approach throughout this journey. Thank you very much for your kind attention. Question please. Sorry, I wasn't so much hurried.
Such a nice talk, but unfortunately, I'm not taking it as a backup. Just after there is a lunch break, so you will be free. You are also free to discuss and interact. Thank you for this. Sorry, but I must congratulate her for such a nice work, definitely very nice work, and very
there are so many fellowships, okay? Nothing is impossible, everything is possible. So please apply the fellowships or contacts and come there, okay? Welcome you all there.
So next talk is by Ms. Khushbu Jain. She is from Haryana, Amity University, and complete free synthesis of pristine CO2 a
There is an oral presentation just for 5 minutes. Please wait for 5 minutes. Then you can go for lunch. Ready now.
A very good afternoon to one and all present here. I am Shivaji, a research scholar in the Department of CBFS at the University of Gujarat. I am going to present my presentation on the topic temporary synthesis of crystalline CO2, important for the catalyst for the MV removal from the water. These are the contents of my presentation. First, I will discuss the synthesis briefly, then the academician part, then some application, and finally the result and discussion. So, this is the synthesis method by which I synthesize medium oxide nanoparticles. I use TABCs. TAB is basically adjuvant which we use in our kitchen. By using the adjuvant, we prepare this aqueous extract, and after treating it with sodium ammonium nitrate, further subjected to precipitation, sanification, and some drying and calcination, we got the sodium oxide nanoparticles, which are basically yellow in color, and these are the some characterizations which we performed. These are the characterizations. First is FTIR, second is XRD. In FTIR, there are many peaks, but the one peak that was that is around 500, that corresponds to CO, which confirms the formation of sodium oxide nanoparticle. This is the XRD spectra of sodium oxide nanoparticle, which coincides with which matches with the JCPDS number 34, which is of sodium oxide nanoparticle. This is the UVDRS studies. In the UVDRS studies, to understand the role of nanomaterial as a photocatalyst, we go for the UVDRS, and the band gap we calculated with the help of the Bell-Common function. It was around 2.89 electron volt. This is the FE7 analysis of the particles who formed, and you can see there is partial agglomeration is there, and some polycarbonate microstructure is obtained. This is the index analysis. In the index analysis, the weight percentage and the attribute percentage quite matches with the molecular formula of the nanoparticles, and there are no any extra means which further confirms the purity of the sample. Now the application, we first degraded the methylene blue dye, and second we did the same for the ibuprofen, which is the drug, and the degradation was found to be around 97% for the methylene blue, and it was around 63% for the EU. The difference, this is the structure of the ibuprofen, and this is the structure of methylene blue. From the structure, it is very clear that MB carries some positive charge on it, and ibuprofen has some negative charge in the aqueous solution. Basically, it is not soluble in the water, it is soluble in some basic medium. In the basic medium, ibuprofen carries some negative charge. Also, the beta study shows that the charge which sodium oxide nanoparticles contains is around -49. So the charge of the sodium oxide nanoparticle is also negative. From this, we can see that as the charge is negative on the sodium oxide nanoparticle, and the charge on the MB is positive. So it is more addicted towards the sodium oxide nanoparticles, and hence degraded to a
for chairing the session. Now all are requested for the lunch downstairs on the ground floor. We are meeting at sharp 2:50 here in this audience.
मैं कहता था कि ये अच्छा एक्सपीरियंस रहा, एक्सपीरियंस मिला, खुद भी आया स्पेशल आए, अगर आपको एक वाला लगे, जैसे कि अगर कुछ नेगेटिव मैनेजमेंट था कुछ, वो कराना था, ऐसा लगा कि बस पता नहीं किसी जगह पे आ गए, इंफेक्शन हुआ, उसके बाद
सब तरह के है एक्चुअली होता क्या है कि ये इस तरह से
Hello. very good afternoon to one and all present in this conference hall, and I welcome you in this parallel technical session number 2, that is on nanoscience and nanotechnology from fundamental insights to functional device. So in this session we will have 2 invited talks and 4 oral presentations, and first invited talk is by Professor Manish Kashyap, who is from Jawaharlal Nehru University, New Delhi. So I will give a brief introduction of Professor Kashyap to you. Professor Kashyap is a professor at the School of Physical Sciences at Jawaharlal Nehru University, New Delhi, and he is a dual gold medalist from Kurukshetra University. He is a PhD alumnus of IIT Roorkee and a postdoctoral fellow from AMES Laboratory, USA. His research focuses on theoretical condensed matter and solar cell materials. He has more than 100 publications to his credit. He has successfully guided 9 PhD students and managed multiple high impact projects funded by various funding agencies like UGC, DST, SERB, AICTE, and title of his talk is Very Curvature Driven Anomalous Transport Signatures in Husler Alloys for Thermoelectric Applications using DFT. So Professor Kashyap, I would like to invite you to give your talk. कॉलर माइक तो नहीं है, वैसे माइक हैंड माइक लेंगे,
कुछ भी दे दो,
हैंड माइक हाँ,
इसको बंद कर दो।
हाँ।
ये भी साथ में रहेगा।
बंद हो गया।
Okay, thank you very much for the introduction, and thanks to the organizers of Shivaji College, especially Anil, Dr. Gaud, for inviting me here and say something about one of my research area, and that is on a new type of thermoelectric effect, that is the perpendicular thermoelectric effect, right? And the topic may be new to you, but interesting also, because you can do your research in this particular area even sitting at your own college, that is Shivaji College, right? And I will touch the dry lab, not the wet lab. When I say dry lab, this means these days we can design the material not only in the actual experimental lab, but on the computers also. Means we can have the computational methods by which we can design the materials in the same way, and it can have the similar type of the properties what you can expect in the wet lab. Okay, so with this, let me start my talk. And the title is Very Curvature Driven Anomalous Transport Signature in Husler Alloy for Thermoelectric Effect using DFT, that is Density Functional Theory. Right, so all these words may be new to you, but we will try to catch some glimpse of these words so that you can find some interest, and if you are motivated to do this type of research, you can come to our lab in GNU to have some exposure on the same.
Maybe you need to ask them. Please go to the next slide.
Okay, this is the content. Why thermoelectric material type and difference, why anomalous nullness effect. You will see this is also the similar type of the effect, but it is seen in a different sense. And the origin of anomalous nullness effect, what is Berry curvature, what type of methodology do we use, and we will touch some of the glimpse of our research progress on Husler alloy and some published papers. Okay, well, you are living in 21st century, and in this century we have the energy crisis, and if it is an energy crisis, so this means you have to produce the energy by some another ways, that is nothing but renewable energy you have to produce. And if we focus in our research lab how we can contribute in the renewable energy sector, so it can be done in 3 ways. We can work in photovoltaic material, we can work in
thermoelectric material, we can work in piezoelectric material. Means with the help of solar energy, with the help of vibration, with the help of heat transform to the electricity, you can contribute to some extent in this renewable energy sector. So that's why, so these three topics are very much important, and out of this in this lecture I am touching the thermoelectric material. Right, so as I said, it is a different type of thermoelectric effect, so it's interesting also in these days. Okay, so thermoelectricity, so we use thermoelectricity in various sectors like thermopower power plant, nuclear power plant, automobile, waste treatment, and factories, natural gas, and so on. No. And wherever you are having the waste energy, waste heat, if you can recover that waste heat, and then it becomes very much important topic and one of the most sustainable application you can target. And by just converting this heat into the power or electricity, then thermoelectric materials helps to improve the energy efficiency and reduce the operational cost, because what we are saying, it is a waste energy, so this means it is available to us free of cost, and if you can convert this one into the electricity, then it is a boon for us. Okay, so now the thermoelectric device are those which are used to convert the waste heat energy into the electricity, right? And thermoelectric effect. So up to your study, maybe up to graduation or post graduation, you are aware of that the thermoelectric effect contains one of the effect that is called Seebeck effect. Fine. So by just making the difference at the two different junction, you can temperature difference, you can produce the electricity. But we are having this is called the longitudinal thermoelectric effect. But we are having the transverse thermoelectric effect, means where you are having the temperature gradient, you are maintaining the temperature gradient in one direction, then accordingly in the perpendicular direction you are going to produce the electricity. So based upon that, you are having the Nernst effect and anomalous Nernst effect. So we'll come to this one. Now let us focus on Seebeck effect. Although it is known to you, let us just glimpse for this. So Seebeck effect occurs whenever the temperature gradient is applied across the materials, and by just producing this temperature gradient, you can produce the electric voltage parallel to the heat flow. Means if heat is flowing in one direction, in the same direction electricity is being produced. But coming to the transverse thermoelectric effect, so see here, so if you are going Nernst effect generate whenever you are having the voltage that is being produced perpendicular to both temperature gradient as well as magnetic field. Fine. So means the two component which is needed for Nernst effect is temperature gradient and second is magnetic field, right? So now if we just try to just check what is the comparison between these two, so you can just see that if we are having Seebeck effect, so fabrication is having the complexity, and there is a size constraint also in this particular one, and reduced performance in metal is there, or gapless system is there due to electron hole compensation. But if we just go with the perpendicular thermoelectric effect, it is having simpler device symmetry, it is better scalability, and few electric interconnect issues are there whenever you are going to produce this effect in the perpendicular direction. So only the limitation is that you required an external magnetic field, which was not needed in the Seebeck effect. Now we have to tackle that how we will take into account the external magnetic field. So it increases the cost and reduce the device efficiency also. But anyhow, so we can eliminate this magnetic effect or external magnetic field, we can eliminate. Let us see how. So to eliminate the need of the external magnetic field, so instead of a system, we can use a magnetic system that is having an intrinsic magnetic field. So we can use magnetic material and their intrinsic magnetism can replace the applied field. Then your Nernst effect becomes anomalous Nernst effect, right? And the benefit is that no external magnetic field is required because it will be supplied by the system only, by the material only. And low operational cost, flexible and scalable device design will be there, and it will be suitable for integrating the thermoelectric device. Now, let us understand this thing with the help of this particular diagram. So, see here, this is a Seebeck effect, means wherever you are having the temperature gradient, in the same directions there is the voltage generation. But if you just see, so this is the hot junction, this is the cold junction, so means heat flow is in this direction, but the voltage is being generated in the perpendicular direction. So, that is why it is anomalous Nernst effect, and this is the Seebeck effect. Okay, so now what is the origin of this Nernst effect, anomalous Nernst effect? So, you can just see that whatever the current is generated perpendicular to the applied temperature gradient in anomalous Nernst effect, which is nothing but analogous of anomalous Hall effect. Let us see how. Fine. So, this ANE is analogous to AHE. Hall effect everyone knows. Fine. So you can just see that ordinary Hall effect, that is caused by the Lorentz force, that is the magnetic force and the electric force, and it required the external magnetic field. And anomalous Hall effect is that which occurs in the ferromagnets, means in the same thing is there. Instead of using the external magnetic field, you can use a material which is already magnetic, that is with the help of ferromagnets. So means in this Hall effect can exist even when there is no applied magnetic field. Now, so as we are saying, so this is the origin of anomalous Nernst, anomalous Hall effect. Just a minute. Okay, so the origin can be explained by intrinsic magnetic mechanism or extrinsic mechanism. If we focus on the intrinsic mechanism, then it can be explained with the help of Berry curvature. This is also a new term for you, so I will explain, of occupied Bloch states, and if it is extrinsic mechanism, that it can be skew scattering or slide jump. So okay, so we will try to have this intrinsic mechanism because we will have the magnetic system. Now, the new term, that is the Berry curvature. So, Berry curvature is nothing but the fictitious magnetic field. So, means you are having a magnetic material and it can have some magnetic effect. So, it is the Berry curvature is nothing but the fictitious magnetic field which can be calculated from the valence band Bloch wave functions, and you can integrate these wave function over the complete Brillouin zone, and it acts as the source of intrinsic magnetism. So, this means there is no need for external magnetic field and you can produce the thermoelectric effect. Okay, so, but definitely, so in order to have the finite Berry curvature, there is a requirement of spin orbit coupling and broken time reversal symmetry. So now let us see what we are having. So, you are having a temperature gradient which will accelerate the electron, you are having a Berry curvature which will produce the Lorentz force because you need the magnetic force, and electron deflects sideways. So, this will produce the transverse current, right. So with this introduction that we need the anomalous Nernst effect. So, how we can implement this one with the help of theory? So, we have the method that is called density functional theory, and there are various computational codes which you can learn very easily. Maybe quantum espresso, maybe VASP, maybe siesta, or in some others as well. So, for example, I am taking the example of a DFT code that is called VASP, Vienna Ab initio simulation package. So, with the help of VASP, you can do the structure relaxation, and then you can go for the self consistency cycle, means you can find the ground state, and based upon this ground state, then you can go for the band structure analysis. You can study in the vicinity of the EF, that is the Fermi level, you can study the various band, that is in the valence band as well as the conduction band. Now, whenever you are having these bands or the ground state properties using the DFT, you can combine the VASP output with the Vernier 90. So then you can generate this wave function, that is multi-level wave functions, and you can obtain the tight binding Hamiltonian based upon this. So if it is available to you, then this can be directly coupled with the Vernier tool, that is again one of the software, and based upon that you can find Berry curvature. So if Berry curvature is known, then Berry curvature is having the formula for the AHC and ANC. So AHC and ANC both can be calculated. Let us see how you will calculate this Berry curvature. And you just imagine, so this is the formula for the Berry curvature. What is Berry curvature? Berry curvature means the intrinsic magnetic field coming from the magnetic system, and if it focus on the nth band, which is in the vicinity of the EF. So, so this is the formula, right? And you can just imagine these terms. So this first term, this is the bracket, you know it. And here n and m are the eigen states of Hamiltonian, and this is nothing but the Berry curvature component of the nth band. So n is there, and this v alpha and v beta is the velocity component along the two direction alpha and beta, right? Okay, so this is the eigenvalues for corresponding to nth band and mth band. So, and this complete bracket represent the velocity operator matrix element between the two bands. What are those two bands? These are the M and the N band. Okay. So now the question is that why I am writing this -2 and LM. Okay. So a factor of 2 is coming so that you can have a correction in the normalization and antisymmetry. And this is imaginary part. Why we are taking imaginary part? Because this imaginary part is coming from the phase difference between the various quantum states, but not with the help of amplitude. Okay, so if you have the Berry curvature, that is this omega, whatever you have calculated, this omega. So if this is known, then AHC and ANC can be calculated. That is the calculation of anomalous hole conductivity. So AHC can be calculated from the Berry curvature by just integrating over the entire Brillouin zone, and it can be weighted with the Fermi-Dirac distribution function, and its relation is given by this formula. See here, so this is known to us, so it is just the simple integration over the entire Brillouin zone. So this means this sigma xy can be calculated, that is called the anomalous hole conductivity. So now, so if AHC is calculated in the same way, that is its analogous part, ANC can also be calculated, and for this one, what we are having, so you have the ANC which serve as the thermoelectric analogous of AHC, and it can be derived from the energy dependent AHC value, and it can be expressed in this way. Fine. So this we have just calculated in the previous slide. So I have given the formula for this one because this depend upon the Berry curvature. So if Berry curvature is known, so this means sigma xy can be calculated. So if this can be calculated, so by this particular integration, so you can calculate ANC, that is anomalous Nernst conductivity. And again it is the integration over the entire Brillouin zone, and you are having the frequency distribution function, that is f, and so here f is the Fermi distribution function, and this mu is the chemical potential, and you are performing the integration over the entire Brillouin zone. Okay, so I will try to explain one of the result using this particular method, and for this we need a magnetic system, and Husler alloy are generally magnetic. Fine. So among the various category of the magnetic materials, so this Husler alloy exhibit the promising properties such as the high Curie temperature, high spin polarization. It can also have the 100% spin polarization. So if you just imagine 100% spin polarization means you are having the bands for one spin channel at the Fermi level and the semiconducting nature on the other spin channel. So if it is so, then it can be used for this spintronic application also. So high saturation magnetization is there, and you can have notable magnetocaloric effect as well. So these materials exhibit the magnetic properties without containing any magnetic entities, right, in the pure form. And the combined effect of the crystal symmetry and spin orbit coupling has made these material very exciting, so that it can be used for the spintronic as well as thermoelectric material. Now the questions come that what type of structure you are having for the Husserl alloy. So Husserl alloy, it can be having the formula X2YZ or XYZ, fine. So depending upon what type of structures you are having. So if you are having L21 structure, that is this one, or you are having the XA structure, so that is having this one. Okay, so we have to focus on this body diagonal, fine. So body diagonal, suppose I take my origin here and this is my body diagonal. So this is 0, 0, 0 and this is 1, 1, 1. So you can find along this line 4 points, that is 0, 0, 0, 1 by 4, 1 by 4, 1 by 4, 1 by 2, 1 by 2, 1 by 2, 3 by 4, 3 by 4, 3 by 4 and 1, 1, 1, right. So along this body diagonals you will have these particular elements, that is X, Y and Z. Okay, so if I just take this CR, MN, SB, so CR, MN, SB will be placed along this body diagonal. And if the position of CR atom is such a way that it is present at 1 by 4, 1 by 4, 1 by 4 and 3 by 4, 3 by 4, 3 by 4, MN and SB are present as 1 by 2, 1 by 2, 1 by 2 and 0, 0, 0 respectively, then you can say that this structure is nothing but L21. But if you are having some different structure, that the CR atom instead of being at 1 by 4, 1 by 4, 1 by 4 and 3 by 4, 3 by 4, so it is present at 1 by 4, 1 by 4, 1 by 4 and 1 by 2, 1 by 2, 1 by 2, means 2 CR atom are together. And here in this case it is CR, then MN, CR, then SB along the body diagonal. But in this case it is CR, CR, MN, SB. So this is called the XA structure, fine. So this is the ordered structure and this can be a disordered structure. So by just replacing the 1 CR atomic position with the MN atoms, so one can achieve XA form from the L21 structure and vice versa. And Husserl alloy, in Husserl alloy disorder are very common, because you cannot study the Husserl alloy without disorder. So that's why from theory side also we generally take into account the disorder in the Husserl alloy. Now the question is that whenever you are designing a novel material, when I say novel material, so this means it is a new material which has not been studied either from the experimentally or from the theory side. So it is very much important to know its lattice parameter, and for this we need to know the energy optimization curve, that is E versus volume plot or E versus the lattice parameter plot. And by just taking the variation in the lattice parameter or volume, right, so you can have this optimization curve which will have the minima at certain points. So wherever you will have the minima, so that is nothing but my ground state, and accordingly whatever the lattice parameter for this one, so that is nothing but a lattice parameter for a particular structure. For example, L21, the structure is this one. For LXA, the structure may be this one, fine. So and accordingly you can have the lattice parameter. Now, so when you have designed these structures, so you have done the DFT analysis, then you can go for the physical property analysis, and it is important to study the dose and the band structure, so that you can just say, because up to this point, so we have analyzed the Berry curvature, AHC, ANC through formula only, but how it will be visualized from the plot side, means from the figure, how you will visualize. So let us see in that way. So this is the density of states for CR2 MNSB Husserl alloy, and we are having the L21 structure, XA structure and B2 disorder, fine. So these are the two structures and this is the disorder, and this is not only the one disorder, but we can have other disorder also. We can have A2 disorder, we can have DO3 disorder, but whenever we are doing the energy optimization calculation, we can just see that which disorder is more prominent, and accordingly we try to design that disorder only. So in this case only B2 disorder was prominent, so that's why only B2 disorder has been shown here. Now see here, so this is the this is for the L21 structure, this is XA structure, and this is for the B2 disorder. And for all the structure you can just see the metallic behavior is there. For example, if you just see, this is my Fermi level, right, and in the Fermi level, so see these are the dose, and dose is dose is having no gap in, this is valence band, this is conduction band. So it is a valid dose is there, so this means it is metallic. But here in the minority channel, means this spin up, spin down. In this spin down channel, so you are not having any dose here, right? So this means you are having this semiconducting type of structure in the downspin, but metallic structure in the upspin. Okay, so this type of material is called 100% spin polarized, and you can just see, so it is written here, the narrow band gap is there in the minority spin scale. Okay, it seems to be very high, but see, just check the scale. Scale is 0.02, 0.8. So this is the very small gap. Fine. Okay, so that's why this narrow gap is there in the minority spin channel, and you can say that in the minority spin channel it is the semiconducting behavior, and so final conclusion is that it is nothing but my half metallic material, right? And in the disordered structure also, this half metallicity remains as it is. That is the robust nature of half metallicity is there. Now let us see what is the effect of spin orbit coupling, because we said that if you need the origin of the ASC or ANC, you need to know what is the Berry curvature, and Berry curvature comes into picture whenever you are having the spin orbit coupling into the account. So whenever you are taking the spin orbit coupling into account, so what happens? So it try to open up small energy gap between the degenerate electronic states, right? For example, okay, just imagine, so these are my two structure, L21 structure and XA structure, and this is without SOC, and this is with SOC. SOC means spin orbit coupling. Fine, focus on this one. So this is L21 structure, and this is the band structure. So what happens? So if I just try to enlarge this particular region, so by just enlarging, so you are having this one. So see here, so if I just check the maxima, what is there? So this is nothing but a degenerate state. Fine. So two bands are there, but these are matching here. Okay. But when you apply the spin orbit coupling, so this gap, this degenerate state will show with some gap. Fine. Same thing is there for this one also. See here, so these degenerate states, but here we are having the clear cut gap among these states, right? Okay, just a minute. So means with the help of the spin orbit couplings, so what is happening? So small energy gap will be there in the degenerate electronic state. So this is the small energy gaps. Fine. Now this will lead to the evolution of Berry curvature. Fine. And whenever you are having the spin orbit coupling energy gap between the degenerate electronic states, so your Berry curvature will look like. See here. So see, this is the band for again the same thing whatever I have shown in the previous slide. And if I try to enlarge it in this way, so what happens? So this is the same graph, and this is my Berry curvature. So see here, so whenever you are having, suppose this is there is no gap in the degenerate state, so means you are not having any signature of this Berry curvature. But whenever you are having the spin orbit coupling gap, then you are having this small gap, and you can just identify that this is nothing but my Berry curvature. In the same way here also. So this I am showing you this one with the different color, that this, and why I am showing here only, why not here? Because it is a band crossing. This is the Fermi level, this is the valence band, this is the conduction band. Wherever you are having the band crossing, only then there you have to just check the what is the Berry curvature. Okay, so means this will give rise into the Berry curvature. So if this is there, so this means ANC and ASC is there, and accordingly you can have the Berry curvature in both the, that is L21 structure as well as XS structure. So this is a magnified view, whatever. So although it is seen here, but it is a magnified view in which you can see it clearly. Fine. Okay. So what is the conclusion? So you can have the spin orbit coupling energy gaps, which is leading to Berry curvature peaks. So that is nothing but these ones, 1, 2, 3, 4, and 3. Okay. So if you have find the Berry curvature, then it is straightforward. You are having the formula for the integration. You will take the integration over the complete brilliant zone of the Berry curvature. You will find the plot for the anomalous Hall conductivity. So this is there, and you can just see for L21 B2 disorder and XA is there, and for all the cases, so it is shown here. So you can just see the variation in L21 is there, this one, and XA is not so much variation, but for disorder and L21 structure, the variation in the Hall conductivity is more. So as if AHC is known to us, so then we can find ANC also. That is our main target. And again the same thing. So ANC can be calculated with the help of AHC. Okay, so if you are having the value for the AHC, then ANC can also be find out. So accordingly, so you will have the variation in ANC, and this is for the 300 Kelvin we are showing, and this is the variation in the anomalous nonus conductivity at EF only. Whenever you are having the with temperature, so how it is changing with the temperature. For example, here it is shown for the room temperature only, that how it is varying, and this is for the temperature at the EF. What is happening at the EF? So it is shown, and up to the 300. So what you can see that the maximum change is in the L21 structure, but and B2 disorder is also having the change, but the XA structure is not having so much change. Okay. So as I have shown you one particular case, in the same way you can have the other cases also, and you can show the Berry curvature. If Berry curvature is there, this means anomalous Hall conductivity is there, anomalous Nernst conductivity is there, and if anomalous Nernst conductivity is there, so this means you can produce the perpendicular thermoelectric effect, right? So let us take the second case, that is nothing but CO2 SC/SB half metallic Husserl alloy. So I will just give you the glimpse only for this one, and so again you are having this similar type of the structure, that is the L21 structure, and XA structure you can also study for this one, and you can find the minimum energy voltage minimum, energy volume minimum, and find out the lattice parameter. So whenever you find the lattice parameter, on that lattice parameter you can run the calculation for the anomalous Hall conductivity, and you can don't think that every Husserl alloy is stable. You have to just check the stability of that Husserl alloy also, and to check the stability you are having two particular methods. That is nothing, one is nothing but the phonon distribution, phonon dispersion curve, and where you should have the all positive frequency. Just imagine, so this is the phonon dispersion curve, and all the frequencies having the acoustic as well as the optical modes. So these are the positive ones. So this means it is stable, dynamically stable, and if we just try to have the AMD calculation, that is all electron molecular dynamic calculation, then you can also prove the thermal stability of this one, and you can study up to the room temperature. So you just see that. So if you have the change in the data with the time. So if you just try to check what is the change in the free energy, so change in the free energy is very small even at the room temperature, and if you check because it is used for the thermoelectric material where the higher temperature is needed, so even for the 900 you can just see a small variation is there, right? So this means it is thermally stable as well as dynamically stable. So you can use it for the further application, physical property verification. So again, so you can just check whether the material is showing the half metallic nature or not, and based upon that you can analyze the band structure. So it is also the similar band structure, but here I am showing the band structure in the two different configuration together, that is upspin and the downspin, or majority spin or minority spin. That is red for the majority spin or upspin, and this black dotted is for the downspin. Just imagine, so you just see that there is a clear-cut difference. So this is my Fermi level. So this black line is not touching with this black line. So this means clear-cut band gap is there for the minority spin, but these bands are crossing with each other. So this means for the majority spin, that is the upspin, right? So this is the metallic one. So this is metallic one, this is the semiconducting one. So this is half metallic. Okay, so if it is half metallic, then we can go for the band structure analysis. Just let us check whether we are having a degenerate state or not. And so see here, so here we are showing the total Berry curvature. Come on. Okay, so total Berry curvature for the lower panel corresponding to electronic band structure. Fine. So this is the see here. So this is the degenerate states, and if Berry curvature is there, so this Berry curvature is there. So this means we can have the ANC as well as AHC, and this can be plotted, and accordingly we can just check whether it is having the significant change in this one or not. So variation of AHC, that is the black dotted, indicate the intrinsic contribution, and the red dotted shows the extrinsic contribution, that is for the anti-side disorder, because as I said, usual alloy or not the actual real crystal, it always contain the disorder, that is the anti-side disorder. Anti-side disorder means wherever you are having the atom, you expect that atom should be at this particular lattice point, but it can be present at some other lattice point also. So accordingly you can have the anti-side disorder, right? So means the side can also be swapped as well. Okay, so if this ANC is there, so this means AHC is there, ANC is there. So accordingly, with the help of AHC, you can plot ANC also, and this is at the this is so this is the blue. This is for the 10 Kelvin. This is for the 300 Kelvin. That is for the room temperature. So for room temperatures, we are having the large variation in this ANC. So this means it can be used for the thermoelectric purpose, and the change dependence of the ANC over the temperature at the EF can be shown here. So you can just see that. So it is going to vary. So as soon as you are going to have at the room temperature, so after that it is not much more variation, but from 0 Kelvin to 300 Kelvin a large variation is there, right? So in this way I have shown you two particular new materials in which you can study the perpendicular thermoelectric effect using the AHC as well as ANC, right? So let me conclude. So whatever I have spoken to you, so we try to explore the anomalous transport coefficient, that is the anomalous hole conductivity, anomalous Nernst conductivity for the user alloy, and in the various structural phases, that is L21 and XA, and we have also included the B2 disorder. So and a large Berry curvature peak has been seen. So these are being originated due to the spin orbit coupled bands, because in the vicinity of the EF you can have the coupling of spin part as well as orbital part, and whatever we have seen that, so one band was occupied, one and another band was unoccupied. Fine, because if you are having the Fermi levels and any band is cutting, so this means on the up, that is on the conduction band side, so it will be unoccupied, but in the valence band it will be occupied, means electron will be present in the valence band, but it can be present in the conduction band through some excitation. Okay, so B2 phase shows the enhanced value of ANC, whatever we have seen in the previous slides, as compared to L21 phase around the EF in both the alloys, because I have taken the example of these two alloys. So these are my ferrimagnetic alloys with large value of the anomalous transport conductivity, and even in the presence of the disorder, the same type of the nature remains persisting, so which makes them a robust thermoelectric material for the thermoelectric application. So with this, let me end my talk. So thanks for your present listening, and if you have any questions, so you are most welcome. They know it better. And there is, I think, some disturbance from the fan also, right?
So I have one quick question. What is the value, experimental value of this thermoelectric voltage, transfer voltage that is generated in such materials?
So these are the novel materials, so no experiment has been performed on these two. Yes.
So thank you very much, Professor, for a very nice presentation.
This is for you.
कोई बात नहीं, मैं इससे बोल लेता हूँ. Hello. So we move to our next talk, that is by so we need to felicitate our speaker, Professor Kashyap. Please come on the dais.
For live live streaming. Okay. This one for live stream. Oh, only for the mic. Okay.
New Delhi. And I would like to give a brief introduction of Professor Ashok Kumar. He is a senior principal scientist at CSR National Physical Laboratory, New Delhi, and professor at Academy of Scientific and Industrial Research, Delhi. He is a dual board journalist and PhD holder from IIT Kharagpur. His career includes faculty roles at various institutes like University of Puerto Rico, USA, and University of Cambridge, United Kingdom. He has published more than 350 research articles in very reputed journals like Nature Communications, Physical Review, and so on. He has more than 10,000 citations to his research articles. And today he is going to deliver a talk on solid state refrigeration, advancing electrocaloric materials for sustainable cooling. So with this brief introduction, I would like to call upon Professor Ashok Kumar to deliver his talk.
Please remind me, 5 minutes before. I don't want to. Okay. Can you little bit switch it off light? Yeah. I don't know. My slides is big or whatever there is no. Okay. So good evening. First, I would like to thank chairman and all the staff member of Shivaji College who invited me to deliver this particular talk. This talk I have purposely chosen in order to have, I can understand that this is college and most of the student belongs to undergrad and maybe postgrad and might be some PhD student also. So this is very good topic for the engineers or the science student who is working in terms of or trying to develop some device, modern device. I'll come to the point. This is also called solid state refrigerator. Why it is called solid state refrigerator, that I will also talk. This is the need of ours, because we have everyone house we have the refrigerator at home, and that refrigerator coolant is emitting CFC, and that CFC is not good for our environment. That creates hole in ozone layer. So European and most of the developed country, they are trying to develop this solid state refrigerator. It's a well-known technique. Theoretically it is well understood, but engineering we have to do in order to improve the performance of the device. So what happened, young man? Down? Okay, everywhere down. Okay. So, in order to start the talk, it's my duty to a little bit talk about our institution. This is one of the oldest institution in India, National Physical Laboratory, where we not only deal with the basic physics, but also we are mandated by the Act of Parliament as a National Metrology Institute, the institute who deals with the measurement. So not only the normal measurement, we have to do apex level measurement. So we all the SI units that is now I don't know how many of you are aware of that SI definition of SI unit is now changed, and now it is based on the fundamental physical constant. So the device which is the follow all the basic fundamental physical constant, that will be only considered as the quantum primary standards for the any kind of measurement. So that we do, and the Dr. K.S. Krishnan, he was our first director. So you know how important this institute is. So if you about me, you can Google me and you can find out what kind of research I am doing. And if you have any query question, you can write me email. So the today talk, I will be talking about electrocaloric effect. This is not only the single effect which used for the solid state refrigerator, but fortunately I was talking with Professor Manish Kashyap. He was worried that there is some talk similarity between you and me, but I found one word that is similar. It's a magnetocaloric effect. I'll come to the point and then I'll talk what is magnetocaloric effect. But the today talk is completely focused on the electrocaloric effect, where this the polar material, polarization used as a cooling material, So the theoretically it was conceived, by the Kelvin, and then later first experimental observation on the ferroelectric material rock salt. So this is what, and then if you look at this particular, the first quantitative measurement was done by this Hertzlob, and then the phenomenological theory, and recently there is a giant, giant electrocaloric effect was observed in the polymer material. So this is the milestone. There are many work has been done. We have also published around, just yesterday I was compiling all the data. We found there are a handsome amount of research paper that I have published since 2026, 2016. So apart from the electrocaloric, there is another, the similar material. I'll come to the point, that's called magnetocaloric. This also related to the spin alignment. The earlier electrocaloric is related to the polarization alignment. I'll come to the point, the physics behind this. Then this is the spin, how to align the spin, and and then flop it, and then you can get it. So this was the magnetocaloric effect, which was also first conceived in terms of the pure iron, and by Emil. Later one of the guy, this Geicu, who got the Nobel Prize also in order to measure the first temperature below 1 Kelvin in this particular method. And then also there are many material, this gadolinium, silicon, germanium, this kind of also magnetical wise, that gave a large magnetocaloric effect. We'll come to the point, all those things, but this was yesterday I generated in order to explain how it can be generated by the Gemini in order to have what kind of the cross relation between electrocaloric effect, magnetocaloric effect, elastocaloric effect, and then the multicaloric effect, means the material which have all these three property. One correlate with the polarization, another is with the spin, and the third is related to the strain of the material. So ideally these two material, all these three materials, we have worked on all these four materials I can say, which is multiferroic and magneto. So this is the magnetocaloric. This is the new area where the property can be exploited by the engineer or researcher, not only the polarization or a spin or the strain, but it can be a cross coupling effect. So this particular material can provide you high functionality. So this is the unique feature of a multicaloric material, and there are many research work is going on in this area. So I started to talking about the electrocaloric, but turn up with the things that the scientific community is trying to find out some material which has all these physical properties, and then these properties should be cross correlated, and that can be used as a functional parameter. So this is the thing that we will talk. Now let's come to the point. We have generated a graphic view in order to better presentation how this machine will work, or it is working I am talking about. So if you look at this, we put the data in the Gemini and I asked them, okay, can you give me a solid state cooling device, how it will be working. So it gave me around, this is very good. So this is the electrocaloric module where you have the fluid which is, so how does it work? So what is the very basic, it's the similar type of the vapor or compressor based, the refrigerator which is every house having. So this, what it took heat from one part of your, one of the, and it release or transfer that heat to the heat sink. So this is the same thing is happening over here, and I'll come to the point. Recently, as per my knowledge, there are some of the, this is the one guy which is in the PTV, I think in Germany, I believe so. They have developed some electrocaloric device, and that can generate around difference in the temperature around 8.9 degrees centigrade. So it's huge. If there is a difference between the 9 degree plus minus, it can be very good useful for the device. So I'll come to the point, how does it work. So let's go to the very basic, and this basic principle is for all these three type of the electrocaloric and magnetocaloric, elastocaloric. What it happens, this is the basic of your compressor cooling system, which is everyone we know is this technology is used by all of us. So what it happens, you compress it, it will increase the temperature, and somehow you transfer the heat, and then if you expand it, it will cool it, gas will cool it down. So then certainly, and then you have to add the heat from the outside in order to make the similar system. So similar thing is happening over here. So if you have, this is the beauty of this particular electrocaloric material, where you can use external electric field as the, so most of the electrocaloric material is called ferroelectric material, it has the inbuilt spontaneous polarization, and that polarization is, is disoriented or rearranged, you can say. So what will happen, you apply external electric field, it will align as well as it will generate heat inside the system. So what will happen is similar to this, it generates the heat, and then what you do, you remove the heat from this particular, transfer the heat into the heat sink, and once you remove the heat, then remove the electric field. If you remove the electric field, again it will reduce the temperature of the material, and now this material will go in contact with the heat element which is in your refrigerator, extract the heat from there, and again transfer to the heat sink. So if this cycle always goes on, and if there is a difference of at least 10 scientists is trying to develop some of this material which having around 15 to 20 degrees centigrade, temperature difference, that will be very good for, and that will be, this is very, very, natural, and this particular material, not, it's a boon for your society. So there are many groups in the world, they are actively working, and many companies, they are also working in order to develop this new refrigerator, which will be based on the solid state refrigerator. So this is the same thing which I have discussed, is the similar thing how this electrocaloric heat pump work. It's the same thing orient the polarization, applied the electric field, it will generate the heat inside that, remove the heat, remove the electric field, it will reduce the temperature of the system. Again, touch with this hot material, it will gain the heat, and then again what you do, the similar reversible process. So this is the all heat pump it is working of this particular. So this is all engineering, and these are the prototype devices. If you want to, one of our collaborator from the Cambridge, they are very, Neil Mathur, he is Indian origin, but born and brought up there. He is the professor. I was there with him for a few months, and he is one of the known figure in this electrocaloric, and from there, so he has everywhere. So another system which is called lead scandium tantalum, this is also multi-layer capacitor. We are also trying to develop this, this having the 6 degree, even ceramic is giving 6 degree change in temperature. But the important part, in India, as per my knowledge, most of the lab, this is very, tricky things, because heat will lose. You will not see the experimentally the change in the temperature. So someone has to, we are trying to develop how we can measure the, in terms of the real. I can skip this. This is the only for representation how this, there is a huge change in the delta T as a function of, applied voltage and in the temperature window. So overall this particular device, which is a module already, used in the system, is working in this. So these are the material where if you can select it and then start working, thought process, someone. So like me, we started thinking how can we can also do some research on this. Can we generate new material which have the high delta T? Delta T means the variability of the temperature. If you apply electric field and remove electric field, apply electric field, remove electric field, and it should have the large change in the temperature, and it should be cyclic in nature. So these are the material where you can say there is an indirect method mainly used in order to see the delta T. I can see, you see. So one of our collaborator, Professor Jim Scott from the Cambridge, he was working on this material with the Neil Mathur and many other groups in the world. He was the coordinator, I can say, all this work. So he was the first person who published the new paper in the Science related to the PGT thin film, and then he saw that theoretically this material has a lot of potential in order to, I don't know whether I have put that paper or not, around 12 degrees centigrade change in temperature. That was the turning point for this electrocaloric research. Earlier it was a thought process, scientifically it is fine, theoretically it is okay, but experimentally it cannot be achieved because it has a lot of loss and other factors, and then you have to do good engineering in order to develop that. So this is the the simple things where this bulk, even the bulk can give you a lot of change in this. If you, the thing is that the most of the bulk system get it has the dielectric background, dielectric breakdown in order to the very small field, less than the 100 kilovolt per centimeter. But if you have the electric field which is large enough, then it can be possible to increase the reversible delta T, and that's the, you can see here it can go up to even the 5 degree Kelvin change in temperature even in the bulk sample, polycrystalline I am talking about. So this is all about the, this is another good work which is published in the Nature, some of the, this guy, Dew et al. And they also observed it can be generated delta S, even the delta T, large, in order to have a kind of heat flux. You can see the large heat flux in this. And this particular work, this is also crystal, because I just found in this is the polycrystalline material, and it has the very good potential in order to have a kind of the large change in the temperature. So now I have given you the brief, understanding about the electrocaloric effect. what is going worldwide, not only the my lab, this lab or that lab. And I have shown you there are various prototype device already available in the market, and there are very active and the research group as well as some of the main company, they are trying to develop that one. So this was the first work that we have started in order to 2016, I can say. And this we found pyroelectric control of the magnetization of this particular, some of the heterostructure that we have developed, like this particular related to the PGT-CFO multi-layer structure, and there are 3-layer structure, 5-layer structure, and 9-layer structure. And this is the basic physics, the Maxwell equation and other things. I'll come to the point that also. And this magnetocaloric is also same. You have the, apply the external magnetic field or internal magnetic field, align the spin, and then generate the heat, remove the heat, and again, lower the temperature. And this cycle will continue in order to have, and this we not only, there are two rays. One is, inverse as well as converse also. I'll come to the point how it is. These two are different compared to, so this one was experimentally carried out on some of our multi-layer structure, PGT, CFO and PGT. And you see, this is the unique in nature. I don't know who is working on this. They know okay, this is not possible. Most of the PGT material is very constant polarization as a function of temperature, and it will be, flop or decrease near the phase transition temperature. But due to this multi-layer structure and due to the strong magnetoelectric coupling, this was flop even the lower temperature. Ideally it is not, it is wrong. We published in Physical Review B, and we argued the referee, okay, this flop in the polarization is due to the strong coupling. It is not due to the, it's very well saturated hysteresis, but once we down to the 100 Kelvin, it is linear, a straight line. And then again if we increase the, and this is by the way very good reproducible and reversible. We went 100 to 300, back to 300, and again we got the similar phenomena. So what does it mean? This phenomena is reversible. So then we went to the check with the external magnetic field, how this magnetic field work for this particular, because CFO is a ferrimagnet material, and then we did all kind of the first loop of the magnetization, applied external magnetic field curve, and if you see there is a various range where you have the 0 to 0.5 Tesla, then we saw how this saturation curve vary, as well as this magnetization as a function of the applied external magnetic field up to 1.5 Tesla and various range. I don't know what it is, it's missing. So then we found this particular system can give a delta T of 1.2 Kelvin. This is by the way published in Energy and Environment Impact Factor around 40 nowadays. It's a very high impact factor journal. So we published that paper where we found it can go down to even the under application of external magnetic field. This is the inverse. This is by the way, this is the beauty of this particular work, where in the lower field you have the positive delta T, but in the higher magnetic field you have the negative delta T. Negative means it's the same system, where it is working for the plus delta T means I was talking about decreasing the temperature, but due to this magnetic field, instead of decreasing, it is increasing the delta T. So this is the first work that we have done, and this is published in Environment long back with one of the, and the similar thing. We also found giant negative electrocaloric effect, and this is all experimental, but derived from not the direct delta T we observed. We derived it from the polarization and the magnetization. Polarization is, as I was talking about, the domain, electric domain, and this is the spin. So this is all related, and here if you see this polarization as a function of temperature, it is going, here it is floppy, it is going decrease and increasing, after that it is constant. And so this is all these due to this we have the different delta S and delta T where we obtain this negative. This is called negative electrocaloric effect. So now you have not only the positive electrocaloric, positive magnetocaloric, positive elastocaloric, but you have the negative electrocaloric, negative magnetocaloric, negative elastocaloric effect, and you can manipulate all those things. So that can be heating as well as cooling also. So this can be used as both device can be used for this particular purpose. And then we also published this work as some of the pyroelectric energy harvesting, and this is high energy density in terms of this particular system. Another work that we done, one of my PhD student over here, we grow this particular, this was also published in JMM. So this was done with the superconducting, where it is, PGT. If you see here, the material is visco. This is the high temperature superconductor, and it was grown on the MgO substrate, MgO, PGT, LSMO, and then in between there was a visco also. So this is the crystal structure or lattice structure, you can say, for the MgO, LSMO, and visco and PGT. What we found in this was good epitaxial fill with the good piezoelectric property, but then also we found it has very good magnetic property. In order to this particular material where magnetization change as a function of temperature like this, and then we extracted these values using the Maxwell equations and other things in order to get the delta S and delta T, in order to see there is a large change, but it's not, delta T is 2 Kelvin, around 2.4 Kelvin, which is generally good, but then effect was new. This was the good, another multi-layer structure we found this. So this is one of the work which recently, one of my PhD students, Charanjit, who work on this, where we got this electrocaloric effect in the PM and PT, single polycrystalline material, where the polarization is varying like this, So this polarization is differential of, polarization is varying like this. So I am not going to crystal structure or the detail, focus will be, completely on the electrocaloric effect. So what we do, we extracted this polarization, extracted the polarization, and then we got the delta P by delta T, and then we found, if you see here, let me go the probably next slide, this polarization, this is the around 0.8 Kelvin, So this is related to the change in temperature for a bulk polycrystalline sample which having this. So I have given you multi of. Recently, we did the same material for the thin film, and then we found this particular material having very good capability. If you make it thin film, this will give you all kind of, as I see, this is good polarization, hysteresis, and the bulk can be becomes relaxer and many things that can be talked later. But the thing is that we calculated all this polarization and then the polarization behavior, and the recoverable energy as well as as a function of this field. In order to see this, so what we did, we checked the polarization under electric field of 30 degrees centigrade and 140 degrees centigrade. There was change in the polarization. We did all this isothermal process, isoelectric process, and then what we found, this can give you both effect together. This is recently published in, I don't know, published somewhere, I don't know where it is published. RSC Advances, just this month only. So this particular paper was dealing with some of the behavior where the same material have shown both property, negative electrocaloric effect and the positive caloric effect. And this is, we have to convince the reviewer, this is due to the change in, polarization up to the phase transition and then the burn temperature. That is another physics that I am not going to talk. So let me conclude my work. What I want to convince you, the only thing, because I understand you are a graduate student, undergrad student, so think something differently. And this is one of the good area where you can have your thought process. this either electrocaloric, magnetocaloric or elastocaloric effect, and design some new experiment, new device where you can really measure the temperature, change in temperature of device, and then it can be integrated as a solid state refrigerator and we can save the nature. Thank you very much.
Thank you very much.
And if you have any queries, question, you can ask, silly question, whatever. Yeah.
Actually, we are getting late. Now we don't have any time. So you can contact him. He works at CSR National Physical Laboratory that is very close to this
Thank you.
college. So you can contact him anytime. We don't have any time to ask questions.
Thank you.
So now it's time to felicitate the speaker.
फोटो क्लिक कर ले भाई तू लाइट तू तो लाइट्स मुझे क्या पता उधर से कर ले नीचे वाले सारे
Two invited talks. Now we have 4 oral presentations. I would like to ask, is Suchitra going to present? Suchitra? No. Okay. So, our first oral presentation is by Dr. Aman Kumar from Shivaji College of
दूसरा माइक कहाँ गया एक माइक का
University. And the topic of presentation is thermoelectric and hydrogen storage properties of RV.
कौन सी बन रही है अभी
Lab
स्टेशन की ये वाली है ना आईडी कौन सा नाम बोला है सर अनंत कुमार क्या
So then we move to next speaker, Mr. Aniket Bharti. Okay. Mr. Aniket Bharti is from Guru Gobind Singh University, Delhi, and the title of presentation is Synthesis Fabrication of MOS2 and WO3 nanocomposite films for room temperature and gas. So, Aniket, as we are running late, so I request you to finish in 7 minutes.
इसको लगवा कॉलर में यूट्यूब
Hello. Thank you so much for kind introduction.
लगवाऊँ यूट्यूब लाइव स्ट्रीम इसको लगाना ठीक यहाँ पे लगा दीजिए पे दे दिए
So I have given, but I don't know what is the reason. Good afternoon to all of you. I am Aniket Bharti from Guru Gobind Singh University, pursuing my PhD under the supervision of Professor Rajesh Kumar. And the title of my presentation is Synthesis, Characterization and Fabrication of MOS2 at the rate WO3 nanocomposite thin films for room temperature NO2 gas detection. Can we have the next slide, please? These are the outlines of my presentation. Initially, I will discuss about the introduction to gas sensor, then the synthesis of the MOS2 and the composite, then basic characterization and gas sensing mechanism, and ultimately at last we have conclusion and acknowledgements. So now initially the
You can directly go to results.
go to results only.
Yes.
Okay. I will complete in 7 minutes only. Okay, sir. So this is the basic working principle of the gas sensor. In the gas sensor, we have the heating plate, then we have the substrate, and substrate we have the sample deposit on the substrate. and the sample which is deposited on the Si substrate is semiconductor, and semiconductor have free electrons, and when the free atmospheric oxygen is interact with the free electrons, the oxygen is absorbed on the surface, and when the sensing gases are interacting with the absorbed oxygen, the electron will release, and ultimately we got the response. These are the synthesis of both the samples. Initially we have synthesized the MOS2 using two precursors, and using the hydrothermal method we got the sample MOS2, and in the same way we have synthesized the composite. Initially we have the WO3 and then MOS2 precursors, and after using the same way we have the MOS2 WO3 nanocomposite. Once we have synthesized both the samples, we have performed the batch sonication of both the sample for the device fabrication during drop casting. This is the method listed below. We have the sample, we have dissolved in different solvent, then ultimately we drop cast it to the substrate. So this is the XRD of both the samples, MOS2 and WO3. Black one is indicating for the MOS2, and all the peaks matches with the standard JCPDS file number 731503. And at the upper side we have the MOS2 WO3 composite, and black one stars are denoting the WO3 peaks, and ultimately we can see that both the samples have in good agreement and matches well with the standard JCPDS of both the samples. This is the FSM of both the sample. In the first one we have the MOS2 sheets, and here we have the composite one. In the composite we have the MOS2 sheets here along with WO3. So this is the basic sensing setup that we have procured in our lab. This is sponsored by DST project, and in this setup we have the two dilution chamber through which we can achieve the ppb level of gas detection also, and these are the cylinders. So once the device is fabricated, then we have mounted a device on the machine, the sensing chamber, and ultimately we got the IV and the sensing measurements. So these are the IV of both the samples. They are going straight, and which shows the ohmic nature of ohmic behavior for both the samples. And this is the selectivity of both the samples, MOS2 and WO3. And in the selectivity, we have seen that both the samples having good sensitivity for NO2 gas and NH3, N2 and other gases also. But it is very high for the NO2 gas, so we can go further for the NO2 gas. These are the gas sensing response for MOS2 and WO3 composite for NO2 gas at 1 ppm level at room temperature. And we have seen that in MOS2 we have the response time of approximately 4 seconds and recovery time of approximately 5 to 6 seconds. And here we have the response time of 2 seconds and recovery time of 9 to 8 seconds. So it is mentioned here in all the things. So baseline conductivity of the composite is very high, which is 462 nanoampere, roughly 230 times higher than the pristine MOS2. That is very good for us because we can integrate the commercial sensor using that, for which we don't need a high precision ampere meter or some kind of things. So these are the cyclability of both the samples, and 5 cycles has been taken, and it shows that the sensor will not go drain, all kind of things are working. Good agreement. At last we have the conclusion. So we have synthesized both the sample using hydrothermal method and XRD for the and IV other things also are there. And these are the acknowledgement and references, and ultimately at last I would like to thank. Thank you so much, sir.
Thank you very much, Nikhil, for finishing your talk in well time. So we can have one question.
Any question? Any questions? Yes, sir. Yes, sir.
Which type of phases are you
Yes, sir.
Which type of phases were found by MOS2?
MOS2 in 2H phase, sir.
2S phase.
Yes, sir.
More stable phase.
Yes, sir.
2S phase is the more stable phase.
Yes, more stable phase, sir.
Yeah.
Yes, sir.
Utilized in gas sensing.
So in the gas sensing, we basically we want more adsorption sites, and we drop cast the sample using MOS2. So few it's kind of a bulky thing drop casting, and ultimately we got the 2H phase from the XRD confirmation. And yes. Any other questions?
Okay, so in MOS2 you are doing some decoration with the help of WO3.
Yes, sir. Yes, oxide,
So,
sir.
can you justify the reason why with the help of WO3, addition of WO3,
Yes, Yes, sir.
Your performance is being increased.
Sir, because WO3 is it's an oxide and it has a higher surface active sites for the absorption, and also the conductivity of the composite is got increases, due to which the baseline current has been increases. It is going up to 462 nanoampere, and in the
Have you seen the similar performance to all the gases?
for all the gases it will not go like that, but we have.
Means your performance is increased with the addition of WO3 for all the gases. Is it so?
What is efficiency?
Ji sir.
Efficiency.
Efficiency is increases for the NO2 gas, and for NS3 also it is quite good, showing quite good, but the signal is very low for as I sorry, in the for NO2 the signal is sensitivity is very high, and for NS3 it is very low as compared to NO2. That's why we have chosen further studies for NO2 only, sir.
And you also need physical justification.
Yes,
for
sir.
explaining all the gases, right?
Okay, sir. Okay, sir.
Okay, so you have shown only the 5 cycles and you are just claiming something. That, okay,
Hey, I am claiming only that up to 5 cycle it is going.
You have to go more.
Yeah, we have to go more up to 100 cycles also, sir. Thank you so much, sir.
Thank you. So, anybody else would like to ask questions? No, then thank you for the very nice talk, Aniket.
Thank you so much, sir.
Can you tell me what is the, how do you sure this is 1 ppm?
So 1 ppm. 1 ppm is basically one.
And sir, if you know that, and how can you say scientifically you have given 1 ppm?
So the machine which we have here using, having the 2 dilution chamber, and it has a software inbuilt through LabVIEW or kind of things.
You go and find out the 1 ppm you need. If you claim 1 ppm,
Yes, sir.
you should know the uncertainty of your values. How it is 1 ppm, 1.1 ppm, 1.2 ppm.
Yes, sir.
It will be drastic change.
Okay, sir. I will for sure check.
So, we move to the last presentation of this technical session that would be given by Dr. Komal from Gautam Buddha University, Noida. And the title of our presentation is Study of the Optical and Electrical Properties of Hexagon and Covalent
डाउन हो गई से ऊपर ही आ गया
So, Dr. Komal, you have 7 minutes.
Good afternoon to everyone. Myself Dr. Komal. Today I am going to give my oral presentation on this topic, structure, optical and electrical properties of HBN tin oxide nanocomposite for non-volatile memories. So this is the overview of my presentation: introduction, motivation, sample preparation and characterization technique, and result and discussion and conclusions. As we all know that we are all surrounded various gadgets such as wearable gadgets, IBS watch, MPX player, pet robot, pocket PC, USB, phone, data, GPS, game entertainment, which involves memory for further operation. So that is why it is very important to search a stable memory devices. So that is why it is very important to work a non-volatile memories. And in the literature, it is clear that the various memories available, such as PRAM, FRAM, PCM, and it is PCRAM and the sorry sir. And this is ReRAM. It is a very important memories. That is why it is ReRAM important memories because it is a fast switching speed, low power consumption and easy to fabrication. So that is why my research work on the non-volatile memories. So ReRAM. So what is the ReRAM? ReRAM is a resistive switching. VRAM is a registry. Sir, ये mic सकते हैं? Okay. So ReRAM is a registry switching random access memory is another class for a next generation non-volatile memories. It is based on electrically induced change of resistance in the metal insulator metal MI structure shown in this figure. So these are the advantages of the ReRAM applications such as excellent scalability, high speed, long endurance, low power consumption, simple structure and CMOS compatibility. So these are the important parameters in the ReRAM applications. First one is the forming voltage, second one is the reset voltage, reset current and current compliance. Forming voltage always greater than in comparison to set voltage and reset voltage. Reset voltage. So there are two type of registry switching: unipolar registry switching and bipolar registry switching. So unipolar registry switching show the low resistance state to high resistance state and high resistance state to low resistance state. Transition depends on magnitude of applied voltage, and bipolar registry switching show the low resistance state and high resistance state, and high resistance state to low resistance state depends on the amplitude and the polarity of applied voltage. So these are the switching parameters that is required for the optimization. So these are the nature of conducting path. There are two types of nature of conducting path. First one is the filamentary conducting path and second one is the interference type conducting path. So filamentary conducting path show that the soft breakdown in oxide layer and also show the unipolar or bipolar switching. Interference type conducting path show the contact resistance changes between metal and oxide, also show the bipolar registry switching. So the main difference between the filamentary and interference type registry switching can be understood by the area dependent of memory cell. So these are the motivation why we choose the tin oxide and HBN as an active memory elements. So tin oxide is a n-type semiconductor material with a 3.6 electron volt is a wide band gap material. So although tin oxide has an important application in transparent conducting electrode and gas sensor, it has gained little attention in these registry switching memories. HBN hexagonal boron nitride is a wide band gap material, layered material with excellent thermal conductivity and electrical insulation, and it also show high chemical stability and mechanical strength, making it suitable for high temperature and nanoelectronics application. So in this figure, okay sir, in this figure we have shown the hydrothermal technique. In this figure we have shown the hydrothermal technique, and also we have shown the how to fabricate our devices by our devices. First we have make a thin film by the spin coating technique. After that we have grow the top electrode by the thermal deposition. Finally we have make a MIM flexible devices, and these are the active switching layer, bottom electrode and top electrodes. That's why we have used in our research work from XRD and Raman spectra. From XRD and Raman spectra characterization, that we have confirmed the successfully synthesize our materials. Further UV visible spectra we have calculated the band gap by the Toc radiation plot. This is the morphology of our materials. We have successfully synthesized our materials. Figure A show the HBN hexagonal layered flakes on its surface, and it also exhibit randomly aggregated HBN sheets. And figure B shows the tin oxide nanoparticles uniform distribution of tin oxide nanocrystalline over a scanned area. And figure C, D and E show that the HBN tin oxide nanocomposite show the tin oxide nanoparticle are uniformly attached to the surface of HBN sheets. These are the one of the most effective tools for determining sample purity of the energy dispersive X-ray spectra. The existence of boron, nitrogen, oxygen and tin species in the HBN tin oxide nanocomposite show in this figure. And this is the X-ray photoelectron spectroscopy. In these techniques, we have confirmed the all materials present in our materials. These are the schematic diagram for the measurement of IV characteristics. Figure B show the real device fabricated. These are the switching characteristics of tin oxide based device. So, tin oxide based memory devices have small hysteresis and higher switching voltage, and the HBN tin oxide nanocomposite memory devices exhibit a bipolar resistive switching, and the 7% HBN tin oxide nanocomposite show the higher INF ratio in comparison to tin oxide based devices. These are the retention and endurance characteristics of our material. These are the results of output. These are the conclusion of our research work. Thank you for listening.
Okay, so nice work first of all. So you have made the nanocomposite.
Yes, sir.
And based upon that, you just check the switching response, right?
Yes, sir.
Tell me the main reason why, with the help of making the nanocomposite, your switching response is being increased. And how you select that which one should be our component of the nanocomposite, so that it can act as a very good switching.
So basically, जो tin oxide materials वो लेस एक्सप्लोर था, और उसमें जो रजिस्ट्री स्विचिंग जो पैरामीटर्स होते हैं जो हम चेक करते हैं, बेसिकली लो कंपोजिशन मतलब फास्ट स्विचिंग स्पीड होनी चाहिए और लो कंपोजिशन होना चाहिए आपका बेसिकली, तो उसमें हाई वोल्टेजेस शो हो रही थी. उस वोल्टेजेस को रिड्यूस करने के लिए मैंने 2D मटेरियल्स को ऐड किया. दैट्स वाई लो कंपोजिशन हो, फास्ट स्विचिंग स्पीड हो, हाई मेमोरी विंडो शो हो. बेसिकली टिन ऑक्साइड बेस्ड डिवाइसेस पे हाई मेमोरी विंडो शो नहीं हो रही थी. Yes, sir.
Right? And there are some established switching elements are there.
Yes, yes,
so
sir.
we try to compare your performance of your device, your composite, with the already established materials. Yes or no? Because if you are having a similar parameters, only then you can say that my device, my nanocomposite can also win the.
सर बेसिकली मेरा जो काम है वो नॉन वोलेटाइल मेमोरी डिवाइसेस बेस्ड था, बट लेकिन टिन ऑक्साइड और विद द 2D मटेरियल्स पे नॉन वोलेटाइल मेमोरीज रिसर्च वर्क बहुत ही फ्यू रिपोर्ट्स अवेलेबल थी. दैट्स वाई वी हैव चूज दीज मटेरियल्स. अच्छा, यस सर.
क्या हमारे पैरामीटर भी उसके आसपास है तो अच्छा है.
Yes, sir.
You would like to ask something. What is difference between volatile and non-volatile memory?
सो बेसिकली जो वोलेटाइल मेमोरीज होती हैं उसमें जो पावर होती है, जब हम लाइट ऑफ कर देते हैं तो उसमें डेटा स्टोर नहीं होता है. बेसिकली पावर ऑफ होने के बाद भी नॉन वोलेटाइल मेमोरीज में डेटा स्टोर रहता है. सर थैंक यू सर.
गए थे अभी। पवन सर वाली है तेरे पास किसकी है?
पवन
आराम से। हाँ
शिवाजी करके अब शिवाजी
शिवाजी नीचे लिख
हाँ
दो
जी
ना।
जी ठीक है ये आप डाल दीजिए दोनों डाल दीजिए इन केस ऑब्जर्व कर जाए चलिए
पवन सर का ये क्या?
पवन सर की ना लिख देते हैं। ये इनकी है।
नहीं ये कुछ ऐसे काटी
पता नहीं इसे सेव किया नहीं किया इसलिए मैं ओपन ही नहीं कर रहा था इसका। अभी सीन पता नहीं है इसका इसने क्या करके आया है। इसने ये किसकी है ऊपर वाली क्या नाम है? सत्येंद्र पाल सिंह, संजीव कुमार शर्मा।
हटा दे
हटा दूँ अभी मिनिमाइज़ करूँ हटा ही दे दूँ। यस मैम।
हर प्रेजेंटेशन जिसकी है जी दास भक्ति उनकी है
एक मिनट
एक है
हम चेक करते हैं।
मेरा प्रेजेंटेशन मिल गया ना आपको? देख
नाम क्या था आपका?
जीवराज भाटी।
जीवराज भाटी मे भी नहीं मिला।
नहीं मेल किया था मैंने।
मेल किया था आप एक बार वो दे सकते हो?
एक बार वो पेन
नहीं ये क्या है? ये उनका एक नया आया है मैंने वो डाल दिया सेव कर दिया शिवाजी ये उनका है ये क्या होता है अभी वही है मेरा
ये रहा ये देखो
किसे भेजा था आपने?
जीवराज भाटी
फ्रॉम
अच्छा नहीं एक
नहीं ये तो एक ही है। हाँ
ये
आप है ना एक बार हमें भेज सकते हैं?
व्हाट्सएप हो जाएगा।
व्हाट्सएप
व्हाट्सएप भेजो वीडियो भेजो नहीं पीपीटी
भेजो दोनों भेज दो कोई दिक्कत नहीं है।
नहीं पीपीटी
8851
अच्छा
8851 099
कौन है जी 42 नहीं जी अभी जी है ना अच्छा तो
42
पवन सर की है पीपीटी पशुपति है
आपका है नेक्स्ट इनका नेक्स्ट तो वो एक सर आए
शायद पशुपति सर या फिर अगला किसका इसके बाद मैं बता दूँगा
एक
इसके बाद इनकी है अच्छा उसके बाद नंबर बताइए
एक है वो मीनाक्षी मिसेस मीनाक्षी कर दो
मीनाक्षी करके चाहिए उनकी
नहीं है आ गई है इनकी पेंट है ना
ले लिया
हाँ ले लिया सुगंधी में है ना ये दे अब तक गलती की भी है मेरे को लगा ज़्यादा हो गया। चल देखते हैं
Everyone, we now proceed with section 3 of the conference. For this section, we are honored to have Professor Pawan Kuleria from JNU Delhi as our session chair. May I kindly invite Professor Pawan Kuleria to take the chair.
वो चल दे ऑडियो वो चल दे ऑन नहीं करते कोई दिक्कत नहीं है।
तो अच्छा चल रहा है, यूट्यूब पे देख ले। तो बंद करना पड़ेगा फिर क्या? अरे 2 मिनट एक्सटेंड पे डाल देना। लाइव चल रहा है ना, 2 मिनट की बात है नहीं, तू लाइव दिख रहा है।
So thank you very much to organizer for giving the opportunity to create this session. And in this session we have total 4 talks. And first talk is an invited talk by Professor Jaising from University of Delhi. So now I will request Professor Singh to
सर की वो खोल दे। हाँ कोई नहीं, ये यूट्यूब स्ट्रीमिंग का।
अच्छा अच्छा अच्छा, ओके। मतलब आई थिंक दिस इज कलर माइक।
दिस इज फॉर पीपीटी डाउन।
या दिस इज
डाउनवर्ड।
अच्छा डाउनवर्ड, ओके।
लेजर लाइट,
ओके, लेजर। Switch off the light. Okay, thank you, Pawan sir, for inviting me here. And first, I would like to thank Dr. Shiv and Mr. Nihal for his kind invitation to deliver some my work. That is not too much recent work, this is very old work, and this talk is totally for the UG and PG student. Okay, little bit I will describe the more detail about the synthesis as well as the more things. Right now I will discuss about two important material, MOS2 and zinc oxide. Both our materials are not very new. That is, material is very old, that in ancient area that will be used for the different purposes. Especially MOS2 used for the solid lubricant in the space, and especially in zinc oxide, that material is used for the as a cosmetic as well as paint and many more rubber companies, they are using the different. But after the discovery of the nano, that will be material is using for the different application. Basically, if you think about the two-dimensional material, that this is a graphene. Graphene is the mother of all carbon structures, and this is the one of the thinnest materials, as well as this is the especially in a graphene has a high mobility, nearly 1 lakh centimeter square per volt per second, and also that will be used the flexible and transparent conducting. And especially in a 2D materials, basically dichromatic materials, and there are a variety of that metallic, semiconductor, superconductor, insulating, and the whole that will be system will be totally dependent on the layer structure dependent property. So these material is for the good for the future, and as also for the use for the different aspects. And basically today I will discuss about this, especially MOS2, and that will be one of the very important material for the TMDC is a field effect transistor, and that is that has the ability to replace the silicon. Basically silicon, if you use the silicon, that we need the 2 nanometer for the device purposes. But if you use this MOS2, 0.65 nanometer is enough for this. This is a 3 times lesser compared than silicon. So definitely that is the reduce the size, the requirement, the minimum size of that, and also the consumption of the power which for the devices. So I will cover these some recent publication as well as this for this, and this is nearly 14 different types of TMDC is available in the nature, that will be having the different property, semiconductor, and that will be insulating as well as the metallic property. So that is very important for this. And you know about this guy Zam and this Roska, that he was discover and the graphene, and he got the Nobel Prize on this, and that the same group were used this two-dimensional MOS2 for this special purpose of the transistor. That time mobility is not too much high. That mobility is only 3 centimeter square per volt. So that he has opened the area for this for the field FET devices. Okay, that why I am interesting, especially in MOS2. Especially in a MOS2 have the very wonderful property. Wonderful property is that will be weakly interact with the layer by layer and weak van der Waals interaction, and that another important property is that will be in a bulk is that this is the indirect band gap. Nearly band gap is 1.2 electron volt. What we tune the size especially in a mono layer, the band gap is the 1.9. This is in the visual range. So due to that, we can use this material for the photo detector, and that will be also there, especially for field emitter transistor. Many more applications we can utilize this material for the, and due to the layer structure, that material also used for the battery application, and also that will be used for the hydrogen production and many more applications that you can utilize for this material. Why I am talking about this for the, especially in a nano electronics. Basically, as I told, this is have the thickness is very smaller, especially in a single layer. 0.6 nanometer is thinner than that for the silicon, and also that will be, we can tune the band gap, and also that will be absence of the bending down, and that more important, this is highly stable. That is the missing in the silicon. That silicon is not too much stable compared than this CMOS2 and WS2. So another important the thing is that will the mobility is very high, that is comparable this silicon, and as well as for any transistor application, you need this is on-off ratio, that will be very good for any transistor device. So this is a 10 power 6. So that we utilize for this purpose. If you know that this crystal structure, basically 3 different types polar type crystal structure is available in the nature, 2H and T types, and this is a rhombohedral, and that will be especially for a hexagonal, and that will be so especially this 2H MOS2 is a more stable structure, and that will be especially in this space goes to PC6MC, and that you can see here, that will be especially about this. And this here, the upper layer is the silicon, is yellow, and that will be in between this MOS like a sandwich between this, and this is the thickness of this nearly 0.6 nanometer, and that will be stacking. And the more important thing, one layer and another is stacking with the weak van der Waals, and but that is the whole system is the covalent bonding of this MO is with the different sulfurs, nearly 4 different sulfurs of this system. So I will talk about this 3 different part of this lecture, and basically first I will want to describe this. We have described we have synthesized the MOS2 by the chemical vapor division, as well as we have deposited the system by the sputtering techniques. All techniques is this is the thin film techniques that will be generated. So for this we have designed our system. This is a 2-step furnace. This is a lower zone furnace. This and there is a higher zone furnace. In a lower zone, basically that is the sulfur. We are using the sulfur, and sulfur is the melting point is very low. There is no need to high temperature. And but especially for MOS2, we have varied the temperature nearly 600 to 850 degrees centigrade, depend upon this is a requirement, our the deposition time, and many more things we are taken here, means multiple option we are taken here, and that we have find out the different. So this is the optical image of that's monolayer and bilayer, tri-layers, but this is not a good way to conclude that this is a monolayer, bilayer. Only for this is a Raman that you can find out the good way, especially for the 2D system. If you are using the graphene as well as MOS2, WS2, that is a good way to recognize and analyze this by this spectra, and that will be here we have deposited different amount of MO3, and that will be, and more important we have taken here, we have used the different amount of sulfur. So sulfur is also important, that will define the pure and MOS2 in a form of this is different thickness as well as the different form. So here you can see the gross structure of this as deposit system. I am not going to detail about this, how to deposit this. Basically we are using our MO3 is a source material, and another source material is sulfur. So then in the presence of the MO2 and this is a sulfur suboxide, then you form this is the volatile suboxide. This volatile sulfide in the presence of the sulfur, that will be sulfurization of this finally we got this MOS2 different layers, and that will be discussed in detail about how to we control this layer by different. So then for this detailed investigation, we have did our experiment for different temperature, 600 and 650, 700, 850. We found that at 600 there is no nucleation, there is no formation of MOS2. That will be, we have found the MO3 and the more MO3 suboxide and many more. When we increase the temperature, that we found the system is at 650, 750, 850 monolayer, bilayer, trilayers, and also we have opted the sulfur amount as well as the temperature, time, many parameters we have taken here. Then we find this is the finally we have observed this is which type of system that will be found. This is only this SCM. You can see here this is there is no complete nucleation here of this is the 650 and this is the 700 and 850 that will find the monolayer, bilayer and trilayers. So if you use some device you can want to divide, that will be very complicated process to transform your film, and this transforming the film is not too much easy, and there is several protocols to formation of this. Then we have synthesized this MOS2 by CVD method, then we coated the PMMA, and then again we have eased our system in the presence of HF for the few seconds, and that will be system will be, and again that will be coated, and that will finally we can, you can see here this is our MOS2 layers, and that for the further characterization for the device purposes we have taken in a new silicon signal oxide for this. So there is whole process for this is for device purposes. If you make some device for photo detector, for field limiter, and any types of system, that will be take some longer times. This will take several times, 24 hours handling, and there are several cleaning process, many more. So for this we need the cleaning area and clean room, and that will be some sophisticated lithography and purpose. This is a wonderful structure. You can see here. This is this is monolayers. There is some defects layer you will find here. This is a bilayer and trilayers, and this you can find here that is a single layer of this MOS2 we have observed here with this HRT and images. And for device purposes, I told we have taken make the photolithography and E-beam lithography. For this, as transfer our silicon, and that we make the contact, and with the help of titanium and gold, and this is the optical image of this, and then we can take this is a transfer characteristics of this mono, especially for monolayer and bilayer. That will be, this will be, and all this will be. So for this we have taken some simple formula for the measuring this mobility of our as prepared sample, and mobility is not too much higher. That is mobility is only 7.6 centimeter square per volt, especially for due to the several defects and impurity in by the CVD methods. Then we have not achieved very good result, especially in this for the field effect mobility of the present sample. Again we moved our sample, we have deposited our sample by this sputtering methods. In this we have taken again two-step process. Here then we deposited our sample MO3, first we deposited, and then that will be sulfurization of the system at a different time, different amount of the sulfur. So there are several protocols we have taken here. Then we will find this wonderful. So this is techniques we have used for this. This is the experimental details. There is, as usual, if you are using this thin film, that will need the cleaning your substrate, and that will be, there are several step process and for this. So for this we are using the here two step. Basically we are using the MO molybdenum that is deposited in the presence of oxygen. Then we find out the MO3 layers, and that after the post-healing of this MO, then we find the MOS2 at different time. Here important thing is here, then we deposit our sample for the few seconds, for the 1 minute, or the only 2 minutes. The whole reaction will be completed, and then after that we have sulfurization of the amount, that will be different amount. So again we found the 0.25 gram is good for the, if you making our sample for the monolayer, bilayer, trilayer. So sulfur amount as well as the time and temperature is the many parameter we have taken here, and that will be. So there is, this is a schematic of this, how to deposit this system MO target, and that we deposited in the in silicon single oxide MO3 layers. Then again MO3 layer move for the sulfurization in the that will be amount of the sulfur as well as the temperature, time, many parameter we have opted here that we find the. So this is again Raman spectra is a very that is good for the knowing to layer, number of layer, mono layer, bilayer, tri-layers. So they are. So we have taken again, that will be, as I told you, we are taken the for 50 second, 80 second, and 100 second, and 150 seconds for this. And again we also sulfurize our sample for the and the presence of sulfur 0.2 gram, and then we found that this is a different layers and different formation. So this is optical and AFM image as usual for the proofing our Raman spectra that our IR deposit sample is that's it. There is the HRTM image the only for the 50 second deposited for 0.21. This is looks like only completely mono layer. This is structure. So for this device versus we again move for the this, and then we have deposited our sample. This is optical image, and that we found that this there, and this will this transfer that will be system that you will find, and that mobility is good compared than our CBD deposit, and that is 21 centimeter square per bolt, and 25 for the mono layer and bilayers and tri-layers. So and this is another important parameter. Current ratio is very high compared than any other reported and minimum. Another important work is that will be we have deposited our sample in a large area. Large area means is a 15 centimeter. So then we have deposited the homogeneous. That is the important things about this. And this that will be here we have taken the MOS2 is as a source material, as a target. We are not using MO as a MO3. So that is very important. But for the purity, for the quality of the crystallinity, we have again we enable our sample for the in the presence of sulfur for the different times and molecule. So as you can see here, this is a sputtered Raman spectra as anneal. After the annealing, that will be crystallinity which is going to high, and that will be at different temperature and different here that we anneal our sample in different time, that in the presence of sulfur, that you can see here their crystallinity is the goods compared than as deposited sample story. So for the best things about the again, then we are taking this Raman data, then we can conclude our sample. There is two basic peak in the especially MOS2, E12G and A1G. E12G is you can see here this is the in plane, this is the vibration of the, this is the sulfur, this is the MO, that is the in different direction, and there A1G is the, this is the sulfur atom that will be vibrated to an opposite direction out of plane. So due to this, there is the number of layer is that will be, there is differences between these position, and after that we conclude that will be then number of layer will be different, that will be peak position. There are differences between the E12G and A1G will be different. You can see here then for the especially for mono layer is a 19 centimeter inverse, then we size will be increased, that will be 24 and 25, that will be especially for in MOS2 system. So again that we have taken this AFM images and for the formation of this monolayer bilayer then confirmed by this system, and wonderful TM images you can see here for this again we have concluded this as deposit simple is a monolayer, bilayer and tri-layers. And that for this finally we move for the for device purposes, then we again move for the lithography purpose, that this is optical image, and that you can see here, and that will be our drain current, and that will be ID and IG, that will be we have taken, we have found here that will be that mobility is very high compared than as reported any other methods. So in these, when we deposit our sample by the sputting and we have used the MOS2 target, for that we have found our good result for the, that will be and especially for especially for this that will be combination of this by post deposition annealing as well as the we can deposit the large area by the especially by this sputting methods, and mobility of this system is nearly 173 to 181 centimeters square per bolt for the this sputting methods. So that is one of the. So another piece of work, this is as I told you, zinc oxide nanowires. So for this we have deposited our sample by the pulse laser deposition technique. This is again wonderful techniques. If you control your structures by different parameters, by pressure of the oxygen, by the temperature of your substrate, and many more things that you can see here. This is one of the control that you can make the device, and that you can think. So this is a protocol for this PLD deposit our zinc oxide that I'm not going to detail about this. As deposit sample is the different times, different temperature, especially for deposit at 500, and this will be 600, and this will be 700, 800, and finally at 800 that we find some cone-like structures. So cone-like structure is good for the field limiter. Again we move for device purposes for this system, and that also we have deposited that our materials 800 temperature for different time, 10 minutes, 20 minutes, 30 minutes. This is a deposit sample is for 10 minutes, this is a deposit 20 minutes, and finally that material is deposited for the 30 minutes. So that will be, then we can complete the nucleation and the formation of the whole structures and whole system that will be. So there is some schematic, this is a possible mechanism for this that is important. And important thing is here we have not used any catalysts for the formation of any impurity of this foreign particles or anything that we will deposit over this silicon oxide substrate, and that will be important things about what is responsible, who is responsible for the formation of these nano cones. So there is very interesting about this. There is formation of this. There is some deficiency of oxygen. This oxygen deficiency act as a catalyst, and that will be formation of the nucleation site that will be created, and the formation of some nano cones of this. Especially for the field emission devices, that is you can see here the J curve, and that will be that in the collaboration of Pune University we did the whole work, and that find the very good field emitter for and beta field enhancement factor is very good 27865. This is the ability of your parameter, ability of your field emitter. This field emitter used for the fat panel display and electron generator source. That we use is FE-SFAM and E-SFAM, and many transmission TEM that will be utilized this system, that material for this purpose. So I want to conclude here that will be we have deposited well aligned zinc oxide nanocone nanofilms grown by this successfully in silicon substrate without using any catalyst, and with the help of this pulse distribution. And also that we find this low threshold nearly 2.4 volt per micrometer, and this field enhancement factor is very good, and 2786. That if you have some question, then I am happy to.
Thank you very much. Any questions from audience?
These are my collaborators, basically, and this is some my publication, and that will be. This is a self promotion. Okay, basically I have several projects I have completed, and right now I am coordinator of DST PERS and DST pairs. And thank you again. Any question? हाँ थक गए हैं नहीं, इसलिए मैंने भी 20 मिनट में ख़त्म कर दिया सर, इसलिए मैंने भी टाइम नहीं लिया. Right, effect of times as well as the effect of temperature, both. Right.
So I think temperature data has been more ideal in this case.
Right.
So what is the effect of the temperature?
Temperature, when we increase the temperature, there is a formation of zinc oxide is very fast. Basically, formation of zinc oxide, that will be nucleation side will be sharper, and then we grown this is cone-like structure. Otherwise, that will be film-like structure. When temperature is a lower temperature, that will be system will be not grow the aligned nanorod or any this type of structure. So temperature is also important parameter for.
How much maximum temperature?
800, sir.
800.
800.
So any other questions from audience? So if there is no more questions, so there is we have token of efficiency from organizer.
सॉरी देखो ये तुम्हारा
So now we will move to the next talk, that is oral presentation, and speaker is Pushpati Pratap. He is from SSP PG College, Hapur, and title of his talk is Silver Incorporated Zinc Oxide Graphene Oxide Hybrid
इससे नीचे होगा
as a high performance gas sensor. So you have 10 minutes time and 1 or 2 minutes before I will begin.
ठीक है थैंक यू सर फॉर इनवाइटिंग मी ये नहीं पशुपति वाला है पशुपति वाला नहीं ये वाला Myself Pashupati Pratap Nirvatan. My topic is AG Incorporated Zano Graphene Oxide Hybrid Thin Film as High Performance Gas Sensor. Content of my presentation is motivation of the work, why we choose Zano Silver and Graphene Oxide, synthesis process, microstructural analysis, determination of functional group, optical properties, application, result and discussion summary. A motivation of the work, Zano thin film have been successfully used as transistor, diodes, gas sensor, electronic, the window layer in solar cell and piezoelectric devices due to their hexagonal wood Z structure. Zinc oxide, graphene oxide, nanocomposite thin film have shown improvement in the performance of optoelectronic, photocatalytic and sensor devices. Zano graphene oxide hybrid nanocomposite thin film have paid great attention due to its antibacterial optoelectronic UV detector, selective properties and CO2 and CO detection. Why we choose zinc oxide? Zinc oxide wide band gap semiconductor, transparent and conductive material, piezoelectric nature, biocompatible, photocatalytic activity, abundant, low cost, tunable properties, versatile forms and wide application ranges. Role of graphene oxide, large surface area, rich functional group, tunable electrical properties, biocompatibility, excellent mechanical strength, unique optical properties, high gas sensitivity, water purification capability and wide application range. Why we choose AG for doping, enhance electrical conductivity, provides antimicrobial properties, improve catalytic activity, modified optical properties, boost photovoltaic performance, supports printed electronics, enhance sensor performance, wide applicability. Synthesis process, we use silver nitrate, zinc acetate dihydrate and graphene oxide dissolved in 2-methoxyethanol. The solution was heated at 60 degrees centigrade, magnetic state, and MEA solution was added drop by 10 drops in 1 hour. Sample were prepared with different AG contents 0%, 1%, 3% and 5%. Solution aging for 48 hours. Spin coating progress, film were coated on quartz using spin coating. Spin parameter
1100 round per minute for 40 seconds. After each coating, films were dried at 150 degrees centigrade for 15 minutes. The coating plus drying cycle was repeated multiple times to control thickness. Quartz substrate was specifically used for optical transmittance studies. Annealed the quartz substrate at 600 degrees centigrade for 90 minutes. These are the XRD analysis, XRD pattern of AZ0. AZ, the nomenclature of sample AZ0 is 0 atomic percent Ag dope ZnO graphene oxide, Ag1 0%, sorry 1%, Ag3 3%, and AZ5 5 atomic percent Ag dope ZnO graphene oxide. XRD pattern of AZ0 and pure ZnO match the wood-jet hexagonal structure with major different planes 100, 002, 101, 102, 110, 103, 200 and 112. Additional Ag diffraction peak 37.8 degree. And 44 degree 200 planes were observed at 3 atomic percent Ag concentration. 8 crystalline size, lattice strain and dislocation density was calculated from XRD using Searles equation and peak profile analysis. These are the FECM analysis. In AZ3, the base FECM structure, micro interconnected structure was observed. This is the FTIR analysis. In it, ZO, ZOAG, CO, COC, C double bond C, OH bond find. This is the Raman analysis. 243 centimeter universe, second order acoustic combination of ZnO, sometimes linked to defect distant activate mode, and 304, 492, 605, 799 and 957 functional group observed. These are the band gap and top plot analysis. Ag dope ZnO 0%, 3.52 electron volt. डोपिंग के साथ बैंड गैप इसमें घटा है, और जो 5 एटॉमिक परसेंट हमने डोपिंग करी है तो इसका बैंड गैप बढ़ा है 3.35 इलेक्ट्रॉन वोल्ट. This is the CO gas sensing. Figure A shows the current volt IV characteristic for AZ3 sensor in dry air and 100 ppm CO at 200 degree centigrade. The IV curves exhibit typical ohmic behavior confirming good electrical contact between electrode and the sensing layer. Unnoticeable changes in electrical resistance is observed upon exposure to CO gas. Exposure to 100 ppm CO lead to absorption and surface reaction on the sensing layer. These interactions modify the free charge carrier density in the material. As a result, carrier mobility and conductivity decrease, causing a reduction in current. This change in electrical transform form the basis of the gas sensing mechanism. Figure B shows the variation of resistance with temperature for AZ0, AZ1, AZ3 and AZ5 sensor in dry air. The AZ3 sensor exhibit a more significant decrease in resistance with increasing temperature compared to AZ0. Ag doping reduces the resistance of ZnO thin film. This is due to the increase in free charge carriers introduced by Ag incorporation. Overall, Ag doping enhances the electrical conductivity and sensing performance of ZnO thin film. Figure C shows the resistance response of AZ3 sensor towards CO gas concentration ranging from 5 to 100 ppm but 200 degrees centigrade. Dynamic sensing measurement was performed using control exposure and recovery cycles. At 5 ppm exposure time was 60 seconds followed by 140 second recovery in dry air. At 100 ppm exposure time was 50 seconds to 210 second recovery to restore baseline. These optimized cycles ensure reliable and consistent sensor response across concentration. Sensor resistance decrease monotonically with increasing CO concentration 5 to 100 ppm. AZ3 sensor shows high selectivity for ppm level CO detection at 200 degrees centigrade. Figure D shows cyclability up to 5 cycles at 100 ppm CO. The sensor demonstrates stable and repeatable performance over repeated cycle. This confirms good long-term stability for practical application. Figure E presents time-dependent resistance profile at different CO concentration. A clear concentration-dependent response is observed with increasing CO levels. The sensor achieves a low detection limit of 5 ppm CO. Enhanced sensing is due to high surface area evident active site. These features promote efficient gas absorption, reaction kinetics and improved sensing performance. फिगर एफ सोच द इसमें सबसे ज़्यादा अच्छी हमारी सेंसिंग CO के लिए हुई है. और This is the gas sensing mechanism. AZ3 thin film gas sensing work mainly through surface adsorption and oxidation reaction. ZNO is an N-type semiconductor and in air it's absorb oxygen molecule on its surface. These oxygen molecules capture electron and form ions. These processes increase resistance by creating a depletion layer. When CO gas is introduced, it reacts with the absorbed oxygen ions. CO is oxidized into CO2, releasing electron back to ZNO. The released electron reduce resistance, which is detected as the sensing signal. AG doping enhance sensing by providing more active site for oxygen adsorption. AG also improves charge transfer and forms a Schottky barrier at AG-ZNO interface. The oxygen spillover effect from AG increase reactive oxygen species on ZNO. These combined effects lead to higher sensitivity, faster response, and better selectivity compared to pure ZNO. Conclusion, synthesis method: AZ thin film prepared via sol gel spin coating under ambient condition. Structural conformation: XRD confirmed hexagonal Burjah ZNO phase with no secondary phase, indicating successful AG incorporation. Effect of AG doping: induced lattice strain, reduced crystalline size, and increased surface area. Morphology: porous interconnector bound like nanostructure with high surface area and abundant active sites for gas adsorption. Optical properties: slight band gap narrowing due to impurity levels and electronic structure modification. Optimized composition: AZ3 shows best electrical properties, defect density, and carrier concentration. And gas sensing performance: significant improvement in CO sensing compared to pure ZNO. Operating temperature reduced to 200 degrees centigrade, lower than conventional ZNO sensor. Sensor response: nearly linear response in 5 to 100 ppm range with fast response and recovery. Overall advantage: enhanced sensitivity, low cost fabrication, and energy efficient operation. Application potential: promising for environment monitoring and industrial gas sensing. Thank you.
Thank you very much for completing within time frame.
Yes, sir.
Please go slide number 8. There is a 002 peak is missing and A get 1 supply. Why? Intensity is very low.
Thank you very much. Yeah, thank you. Next speaker is Ms. Meenakshi from Central University of Haryana. She will speak about low temperature magnetic transfer, magnetar chlorine performance of soldier, derived GD and DCR analysis.
ये उसका लाइव स्ट्रीम यूट्यूब पे अपना
गिर रहा है बार बार, वो गिर रहा है। इस आगे कैसे होगा?
ये इससे नीचे का और माइक ऑन कर देना बटन दबा के।
So Meenakshi, you have 10 minute time.
Yes.
Please try to complete within time.
Good afternoon, all of you. My name is Meenakshi. Today I am here to present my presentation on the topic of low temperature magnetic transition and the magnetic caloric performance of sol-gel based double perovskite compound. So these are the content of the today's presentation. Start with the introduction, the synthesis method and the results and discussion, and then finally we have conclusions. So start with the magnetic refrigeration. Magnetic refrigeration is a cooling technology which is based on the magnetic caloric effects, where the material's temperature change when exposed to the change in the magnetic field. So why we are using magnetic field? Because of course there is no gas, harmful gases are used, so which is used in the conventional refrigeration, so it is eco-friendly, there is no compressor used, so it is a noiseless and of course it's a high efficient as compared to the gas based. Okay, and the cost effective. So what is the main phenomena of the magnetic refrigeration? It's the magnetic caloric effects. Here we can see that this is the phenomena where the magnetic materials experience a change in the temperature. Like when we magnetize the material, the magnetic materials get hot, and we demagnetize the material, it become cool. So what is happening? In the magnetic material there is a domains. We can see in the first stage there is a magnetic domains present. After we magnetize the material adiabatically, all the domains are like all the moments, the magnetic moments are aligned in the magnetic fields, so the randomness is decreases. So the entropy of the material is decreases. Randomness decreases, entropy decreases. To compensate overall the entropy of the system, the materials get heat up, so the temperature gets T plus delta T. All that extra heat is expelled by the heat exchangers. Now that we have the temperature T and all the domains are aligned, now demagnetize the material, so all the domains are again randomly organized. It means ki randomness is again increases, so the entropy of the material, magnetic entropy is increases. To compensate overall the entropy of the system, the temperature of the material get cool. So we like this, we produce the cooling. So this cycles complete and we get the cooling. So how we can find the magnetic caloric effect? So these are the two parameters we can we can see that this quantify the magnetic caloric effects. So first is the change in entropy and the RCP, the relative cooling power. So the change in entropy gives the cooling efficiency of the material, cooling capacity of the material, and relative cooling power gives the cooling efficiency of the material. So from the Maxwell equations we can find the change in entropy, and after we can find the RCP value. So we need those materials which having the high change in entropy and the RCP values. So one of the material is perovskite materials. So perovskite materials are discovered by the Gustin Ross in the Ural Mountains in 1839, and the name of the perovskite is given by the honor of the Russian mineralogist Lev Perovsky. So the perovskite having the general formula of AbO3 structure, where A is the trivalent cation and B is the divalent cations, and the general formula for the AbO3 structures, this is the structure for the AbO3, where A is set at the corner of the cube, B at the middle of the body centered, and oxygen is the face of the. Now to enhance the property of the single perovskites, the double perovskite is discovered. So where one of the B element or one of the A element replaced by the another of B or A element, so it becomes the double perovskite oxide. And for the stability of these perovskites are predicted by the tolerance factor. This is the formula for the tolerance factor, where Ra, Ro, Rb are the different ionic radii of the material. For the tolerance factor for the cubic, it lies with the 0.9 to 1. For the orthorhombic and monoclinic structures, it lies from the 0.75 to 0.9. Now why we are using perovskites? Because of the physical structures, the chemical stability, non-toxic. These materials show candid endoferromagnetism below the transition temperature. Because of we are using the rare earth at the A site, so the high magnetic moment. So because of the high magnetic moment, these materials show the large entropy change and the high RCP values. These materials also show low hysteresis, means low energy loss. These materials also show different kind of interactions, and because of these interactions, they can be in different applications. Like we are here focusing on the material show the high magnetic caloric value, so you can use in the solid state refrigeration. So these are the application or different for the magnetic caloric. So these are the application for the perovskites. Now the synthesis process of the compound. So all the precursors are taken in the nitrate form mixed with the diwater and citric acid and ethyl glycol. We are stirred for the 80 degree at 6 hours, and then we get the gel formation, dry the gel, we get the puffy mass. after ground the Pruffy mass, we calcined it in the in 800 degree. After that, we get the sample, and then we get the pellets, and we centered that. This is the process for the compound synthesis. Now the characterization. For the structural analysis, we done the XRD. For the morphologic analysis, we done the IC-SFAM and IDEX, and the magnetic analysis done with the PPMS. So results in the discussion. Start with the structural analysis. These are the detailed refinement XRD pattern of the sample. We can see that there is no secondary phases or secondary peak present, so they are monophasic nature. The compound exhibits orthorhombic structure with the PB-NM space group, which we find from the reticle refinement. From the crystal, the average crystal size of D was calculated by the WH plot. From this we can see the D values 60 nanometer we get. These are the parameters which are found from the reticle refinement. Now the morphologic analysis, we can see that this is the IC-SFAM image of the sample. They are nearly spherical in shape with the homogeneous throughout, and the average particle size which is 2.3 micron. And this is found from the images software. The magnetic analysis, from there we can see that this is the empty data for the compound at the field of 100 oyster from the both ZFC and the FCC field. Here we can see that in the higher range, both the curve is overlapping, which means that in the higher temperature the materials show the paramagnetic nature. As the temperature decreases, both the curve are bifurcated, and we can see that further we get the first transition where the antiferromagnetic ordering because of the chromium and the manganese we can see, and due to the superexchange interactions. After this, the curve after the range from 11 to 57, we can see the ZFC and the FC curves are separated, and this is because of the candid antiferromagnetism, and which leads to the weak ferromagnetic magnetism. Now after the or reduce the temperature, we get also another transition at the 11K. Here we can see that this is because of we are doping first A site on the rare earth, so because of this we get the transition, and all these transition we can find from the dm by dt curve. After that, we done the magnetic caloric analysis. From here, we find the magnetic caloric analysis from the MH loop for the first quadrant at this range from 3 Kelvin to 60 Kelvin. And from here, from the change in entropy, Maxwell equations, we find the change in entropy value, which is 9.94 at 7 Tesla. After that, we find the relative cooling power for this formula, and we will find it range from the 220 at 7 Tesla. So this is so these results make these materials can be good for the magnetic refrigeration from these values. So conclusion, we have successfully synthesized the sample with the sol gel and the reticle refinement confirm the single phase nature, and after the IC-SFAM analysis, this has the spherically grains we are found from the IC-SFAM images, and the magnetic studies revealed the two transition temperatures and the higher range it become the paramagnetic, and the lower ranges it become the antiferromagnetism, and so on. And that this compound also a large change in entropy and RCP value, which is promising for the eco-friendly candidate for the magnetic refrigerations. So these are the reference for the work. Thank you.
Thank you very much. Already it is the time. So now session is open for any question.
Can you tell me, suppose that if you want to make a refrigerator of this particular material, how good and how can you imagine to have a refrigerator in this particular material?
So maybe this material is not that great for making the refrigeration in actual. That can be used, sir. Okay.
So the thing is that's fine, you understand. So the thing is that you require nearly 7 Tesla or 2 Tesla, 7 Tesla for having certain change. So practically it is very
Yes, sir. Yes, sir. I can understand.
So I think you can look at the material which can align and maybe give more delta T in the very small
magnetic field, yes sir. Practical. Thank you sir.
Thank you very much, Meenakshi again.
Thank you sir.
Now we will move to the next presentation, that is by Mr. Shivaji. So he is from IIT University, Rajasthan, Jaipur. Mr. Bhati will speak about development of epoxy-based polymer composites reinforced with marble powder for protection against high energy electrons. So he is the last speaker of this session. Mr. Bhati, you have 10-minute time. Now you can
Good evening, everyone. Hello. Myself, Shivaji Bhati. I am a PhD student in Manipal of IIT University, Rajasthan. And maybe sir might not know, but my internship was in IUAC. At that time, I known to Pawan sir, and I am glad to meet you. Thank you. And so today my presentation of topic is radiation shielding characteristic of particle reinforced polymer composites. So first we will discuss that why we need shielding from radiation. We know that ionizing radiation are used in medical industry and research, but since they are harmful for radiation, we need to shield them. Conventionally we were using lead and concrete for shielding purpose, but there are many drawbacks, like they are heavy and lead is toxic. So here we need eco-friendly and lead-free lightweight shielding materials. For this I have used iron ore and for low-cost radiation shielding fillers. The iron ore, it is incorporated in epoxy, and then we have prepared a sample, and that sample we have used for shielding purpose. The iron ore which we have used, we have taken it from Shahpura, Jaipur. There is some industry. From there we have taken, and for checking the shielding, we have used a linear accelerator, medical linear accelerator, situated in Manipal Hospital, Jaipur. And we have used electron energy from 6 to 15 MeV, and we have also developed graded epoxy iron composites. So this is how we have prepared the sample. Iron ore is mixed with epoxy, and after further mixing we have added a hardener, and after mixing we have poured it into steel mold for curing purpose. So this is a schematic diagram of a medical linear accelerator, and this is farmer chamber, Marcus chamber, electrometer. These are slabs. These we have used for measuring the how much amount of radiation is coming. So the sample which we have used is powder magnet, 30 to 80 micrometer iron magnet, more than 80 micrometer iron, and 30 to 80 micrometer iron non-magnet. Actually, the thing is, we have taken these sample, taken these directly from the industry. They are not much prepared. This thing I am telling because we are not processing the iron. We are simply using the iron ore, and simply by using the iron ore, we are making the material. So it becomes very low cost. At present, these are very costly. The lead apron which we used in hospital, they are costly. We try to make some sample which is very low cost and also lightweight. So the linear attenuation coefficient which we measured, then we found out that it is highest for the powder magnet in photon and as well as in electron, and the mean free path, half failure and 10th failure, they are lowest for powder magnet. So here we conclude that the powder magnet is good among all others for attenuation. The linear attenuation coefficient is decreasing with increasing electron energy, and mean free path, half failure, 10th failure, they are increasing with increasing electron energy. So as it is increasing with the increasing electron energy, we can know that it is not much significant for high energy electrons. So since in previous slide we have noticed that the powder magnet is better among all other samples, and so we have in another sample we have increased the weight percentage of iron and decreased the weight percentage of polymer matrix. So here we got to know that as we are increasing the weight percentage of iron, the linear attenuation coefficient is increasing, and the mean pay path, half failure, 10th failure, they are decreasing with increment of weight percentage of iron. So as we are increasing the weight percentage of iron, the shielding is increasing. So in these two slides we have concluded that powder magnet is better among all other samples, and also when we are increasing the weight percentage of powder magnet in sample, then the attenuation is increasing. And further we have prepared a sample which is from one side that is epoxy rich and on another side that is iron rich. So when the radiation is coming from epoxy rich side, and another test when is radiation is coming from iron rich side. So the result was that when the radiation is coming from iron rich side, the attenuation is more, even the sample is same. So but here is the difference in directional behavior. So the difference in directional behavior, it is decreasing with the increment of electron energy. So it is less significant for high energy, but it is more significant for lower energy. So the mean pay path, half failure, 10th failure, they all increase with increasing the energy, and the radiation shielding efficiency, it decreases as the electron energy is increasing. So when the electrons are entering from iron rich sides, at first they are facing the higher density and higher Z material. So earlier there is strong scattering and rapid energy loss, but when they enter from epoxy rich side, at first they face lower density and electron travel deeper before interacting with the dense region. So the key points are powder magnetic, it has shown the highest attenuation. It is because of high density, better packing, interfacial bonding, and the gradient composite which we have prepared. On one side it is iron rich, on one side it is epoxy rich. There we have checked that it is showing the directional behavior. On one direction the attenuation is less, on another side if the attenuation, then attenuation is more. So as per discussion, the addition of iron ore to epoxy resin significantly improve the radiation shielding of epoxy. As the amount of iron ore increased, the amount of high atomic number in sample increased. So the filler types, our matrix is epoxy, filler type is iron ore. So it strongly affects the shielding, and graded structures, they show directional behavior. So the advantages of this is it is low cost, it is easy to manufacture, it is eco-friendly, and it can be used for shielding of electron energy. So it is lightweight, non-toxic and lead-free. We can use it for high energy electron in like linear accelerator, medical linear accelerator or industry. And future scope is photon shielding multi-layer gradient structures. Applications are in medical, industry and research. These are the references. Thank you.
Thank you very much, Mr. Ravi. So can you be able to explain like how electrons are interacting with the materials? Because any material that you can select for radiation shielding, so that will depend upon interaction of the electron with the material.
Yes sir, yes sir.
And that interaction process, I think, again depend upon the energy that they are going to use.
Yes, yes.
So in this case, like in last slide you have proposed that the same magnet can be used for the photon also.
Photon?
Yeah, photon gamma rays.
Yes, yes.
Because interaction of the gamma ray is different, interaction of the electron is different, and interaction of even
one experiment I have also done with the photon also, that also graph I have shown. But for photon energy, we need to use larger thickness.
Yeah, that's fine. But how they are interacting with the material?
Like when a photon is interacting on the epoxy material, at first it will it will interact with the electron, and the electron will release, and that electron it will go and it will go like there is a PDD curve, like percentage of those, like the graph is like if photon, then for photon the surface energy is low, but for electron the surface energy is high. Like the electron, for electron the graph is like this, means the surface energy is more, but for photon, like for electron it will start from 85-90% of surface dose, but for photon it will start from like 40-45%, and it will also decrease with increasing the photon energy. So and the dose of maximum dose is for photon, it is like the Dmax, it is more for photon, but it is less for electrons, and the photon will go far deeper in the far deeper in that sample, but electrons they will stop very early.
But only simply interact like there are three processes. Photoelectric effect, Compton effect, and pair production.
Yes, yes, yes.
The rest of them will interact.
Yes, yes.
Similarly, electron will interact.
But here in my
interaction process entirely different.
But here since my energy is more, so the photoelectric effect it will be less dominant in like for mega electron volts, photoelectric effect it will be less dominant, but the Compton and the pair production they will be more dominant here.
But in this case, you are using electron.
No, for photon I am telling.
Okay, no problem. So any other question? So now then, thank you very much.
So similar thing, I would like to add on the what has things. What is the basic mechanism? You can put anything bigger inside that, any metal, iron ore, aluminum ore, any ore, even the, you can put the mud inside that. That will also impact. So the thing is the mechanism. What is happening? Why this your iron ore is important in order to have the interaction, and what is in terms of the attenuation, in terms of the basic.
Like iron is a high Z material, and it is having a large number of electrons. So due to those electrons, there is more scattering. When the photon electrons they are coming, the scattering is more because of that high Z material. That
is fine, but if it is your area, you go, and that is the important thing, that you have to have a real research understanding of your application. So go and rethink on that, why it is important, because this is the only, cost is not the matter. Once it is real application, if you go, that is one aspect. But the important part is to know the real physics, what is happening inside. So that you will understand, you can improve your, this is very good, by the way, very good as per my understanding, this is very good for application point of view. So improve this one, and that will be very
interaction of electrons with matter, electrons of photons with matter.
Why not other material?
Any material that you are going to use it, how electron is going to interact with the electron.
Thanks.
That you understand, then you can easily select which figure you need.
Be an expert,
Yes, sir. Thank you for the feedback, sir.
Thank you very much. And with that, we can conclude this session, and I will hand over to the audience.
Oh, sorry.